welcome to this crash course on statistics. It's a little over 4 hours, so if you thought that Oppenheimer was long, well, wait until you see this one. Here's what you're going to learn. You're going to learn about inferential statistics, confidence intervals, and as well hypothesis testing. So all things that are fundamental and paramount to statistics. And all of that you're going to apply using Excel. Now, a few things that are important for you to know. The first one is that if you truly want to follow this crash course, there's the course materials that you need to download. There's a link in the description, and as well I'll put it as a comment of this video. The second thing that you need to know is that if you finish everything, there's a tiny gift for you at the end of this crash course, so a little nugget for you to keep you motivated. And then the third one, which is also a second gift, is that I'll share one of the most motivational quotes that I've ever heard, and I'll do it at the end of this video. That being said, I wish you the best of luck. It's a little over 4 hours, but hopefully you'll find it a lot of fun. I'll see you then. Welcome to the key statistics section of this online course on statistics. So what we are going to cover is a variety of statistical measures and how to use them to analyze data. You'll start by learning the measures of central tendency, and this includes the mean, the median, and the mode. You'll then move on to measures of dispersion. And this means something like standard deviation, variance, and then what happens is that we learn about the normal distribution. We cover as well the covariance and the correlation. And most importantly, we focus on practice. So we use Excel to perform these calculations. Throughout the course, you'll have the opportunity to apply what you have learned through exercises and quizzes. And to really test your skills, there's also practice tests at the end of each section to help you solidify your understanding of the material. So let's get ready to dive into the world of statistics. Until the next video, have fun. This video will focus on the types of variables that exist. Now, you likely have heard of ordinal or continuous variables, yet you just might find them a bit confusing. The goal is to provide you with a framework so that you can clearly distinguish them. Variables can be split into two, quantitative and qualitative. If we start with a quantitative, there are two types. The first one is continuous, and examples would be age, income, or how many square meters a house has. Any metric that measures or quantifies falls into the quantitative continuous bucket. The other type is discrete, which is continuous variables that are grouped. For instance, instead of age, you can consider groups between 18 and 25, 26 and 34. Another example is that you can also group income in buckets, like buckets of 20,000, like between 0 and 10K, 20K and 30K, and so on. On the other side, we have the qualitative variables, which also have two variants. The first one is nominal, and an example is the color of people's eyes, so blue, green, or brown. A second example would be the type of room in a house, bedroom, bathroom, living room. A nominal variable is something that does not have a natural order. The second variant will be ordinal, and by opposition, there is a natural order. For instance, when people finish their education is a good example. So we have middle school, high school, bachelor's, and one follows after the other. Another example is survey data, where you have scales of 1 to 5, very unsatisfied to very satisfied. Again, the values don't have a meaning per se, but there is a clear natural order in how they're set. And when we talk about nominal variables, there's not a natural order. So if we think about the color of people's eyes, the color blue is not necessarily better or worse than the color green. Therefore, they're nominal variables. They exist, but we cannot really rank them. And with ordinal variables, we can rank them. To sum it up, variables can be quantitative and qualitative. Quantitative is split into continuous and discrete, and qualitative into nominal and ordinal. This is it. Till next video, have fun. In this video, I'm going to talk about the difference between samples and population in statistics. A sample is a subset of a population. Now, let's use an example to illustrate this. Imagine that you're trying to understand the eating habits of all the people at your company. The entire group of individuals at the company is called the population. If you were to survey 100 colleagues out of the thousands at the company, the group of 100 people would be the sample of the population. It is important that the sample be representative of the population. This means that the characteristics of the sample should match those of the population. For example, if the population of colleagues at the school is evenly split between males and females, then the samples should also be evenly split between males and females. If the sample is not representative of the population, then the conclusions you draw from the sample may not be as accurate for the entire population. For example, think of this burger as the whole population. A representative sample is taking a bite out of the whole burger. A non-representative sample is eating just the burger or the bun or the salad. Moreover, it is often difficult or even impossible to study an entire population. For example, it may be too expensive or time-consuming to survey every single colleague at the company. This is why it is often easier to study a sample of the population instead. However, it is important to carefully choose a sample that is representative. Otherwise, the results of the study cannot be accurately applied or extrapolated to the whole population. So, I hope these examples have helped to clarify the differences between samples and populations in statistics. Remember that a sample is a small subset of a larger population, and it is important to ensure that the sample is representative of the population in order to draw accurate conclusions. Moreover, it is often easier to study a sample rather than the population, and this is what we do 99% of the time. This is it. Until next video, have fun. Welcome to the case study briefing on a burger restaurant. And in this case study, we'll be examining data on customers of a burger restaurant, and they sell 8 different types of burgers. And this includes a cheeseburger and a bacon burger. The data we have is at the customer level, and it includes demographic information such as gender and age. And throughout this case study, we'll be showcasing various statistical concepts such as the mean, median, correlation, standard deviation, and more. Now, these concepts will help us better understand and analyze the data we have on our customers. We'll kick it off by discussing the mean, which is the average, right? They're the same thing. They are a measure of central tendency, and it is calculated by adding up all the values in the dataset, dividing by the number of values. Now, what does this mean exactly? So, for instance, in the context of our burger restaurant, we could find the mean for the revenue of burgers sold to customers of a certain age group. This could be something that is insightful. Now, there's a lot more here, and this will be our practical case study. And I'm actually super excited to show it to you. I think it's a fun data set to play with. It's challenging. And yeah, let me not spoil you further. Till the next video, have fun. One of the most important topics in statistics is the measures of central tendency, the mean, median, and mode. Now, you most likely have learned them before, and you might be considering to skim past these lectures. However, I bet that you or the people around you use them wrong, especially the mean and the median. Now, I would ask that by the end of this series on the measures of central tendency to let me know if I managed to actually teach you something new. The measures of central tendency are essential statistical tools that provide insight into the center or typical value of a dataset. These measures help to summarize the data, making it easier to analyze and understand. The three most common measures of central tendency are the mean, median, and mode. Each of these measures offers a unique perspective on the central value, and understanding their differences and applications is crucial for accurate data analysis. I always say that it's very important to understand what a KPI or a technique does, and even more important, what it cannot do. So if we kick it off with a mean, it's often referred as the average. It is the most widely used measure of central tendency. To calculate the mean, simply add all the values in the dataset and divide the sum by the total number of values. The mean represents the arithmetic average of the data and is highly susceptible to the influence of outliers and extreme values. And despite this sensitivity, the mean is an incredibly useful measure in various applications, particularly when dealing with symmetrical or normally distributed data. Moving over to the median, another measure of central tendency, represents the middle value of the dataset when the values are sorted, and it doesn't matter if it is ascending or descending order. In cases with an odd number of values, and as I'll show you, the median is the middle value. And while for datasets with an even number of values, the median is calculated as the average of the two middle values. I'll help you visualize this when we look at the median lecture. To finalize on the median, it is less sensitive to outliers and extreme values, and it makes it a more robust measure of central tendency when dealing with skewed data. And more often than not, we do have skewed data. Finally, the mode is the value that occurs most frequently in a dataset. In some cases, there may even be multiple modes or even no mode at all. The mode is particularly useful when we are working with categorical or discrete data, as it highlights the most common value or category within the dataset. However, the mode can be less informative when dealing with continuous data, especially if there are numerous unique values. To conclude, measures of central tendency play a pivotal role in data analysis because it provides a snapshot of the central value or the most typical value within a dataset. They are a starting point to become one with the data, to get to know it. And now we are going to deep dive into each of them. Until the next video, have fun. Hey everyone, and welcome to the mean video. And yes, that was a very poorly constructed statistical pun. The mean is the most common statistical concept. We use it everywhere to describe people, objects, monuments, and even as an adjective. How many times after being asked how your lunch at the restaurant was, you replied, yeah, it was fine, it was average. At that moment, you're using statistics to describe your meal. One crucial fact is that I'll use mean and average interchangeably. And the reason is that they are synonyms. There's not one hidden special meaning that mean has and average does not. However, there's many types of means. When people say mean, they refer to the arithmetic mean. You may likely have heard of geometric or harmonic mean at school. The key idea is that it was only at school. I've never used anything other than the arithmetic mean in any professional setting. From a mathematical perspective, to compute the mean, you add all the elements, which is represented by the numerator, so this xi. The inverted e means a sum, and the xi are the values. After you sum all of them, you divide by n, which is the number of instances. The mean is one of those KPIs that, when presented, can be technically correct and grossly misleading. Imagine that you are at a house party and you are with 8 of your friends. You are decently well off in life and each of you makes $100K. That means that the average income is $100K as well. Now, you have a surprise visit to the party. Elon Musk comes in and let's imagine that his income last year was 10 billion. The average yearly income at the party now rose to 1,090,000. Now, saying that each person at the house party earns over $1 billion is technically correct, but would be grossly misleading because you have one person in the room that makes 10 billion and the rest only 100,000. Oh, and by the way, Elon Musk here would be considered an outlier, which is a data point far different from the rest that can skew the analysis. Therefore, it is best to use the mean to describe data when you have continuous data and the distribution is symmetrical, like in this image, without outliers, or the data is not skewed. Let's have a deeper look as we explore this section, as we explore the median. We are done. Let's now put this into practice. Until the next video, have fun. Hey everyone, let's kick off our practice journey. In this video, I'll show you how to download the course materials in case that you have not done so. And we'll also do the first exercise on the mean. The materials, you'll find it here on lecture 3, important download course material. You have the resources part, just click on it and it will immediately start to download. It will appear if you use Google Chrome. It will appear in the downloads part of the browser. Now, as you get there, you'll get this file folder. Me personally, I have stored it in my desktop, but you can store it anywhere that you want. So I'm going to go to my desktop and you'll see it here. Let me open it and then I'll go to the key statistical concepts section. That is the main one here for this section. And then you have this burger joint file here. Please double click on it so that it can open. I'll give you an overview on top. Aside from the Excel file, you also have this description of the data set. If you click on it, then once it loads, you'll get to see a brief description of the data set, in bold the most important thing. So we have a sample of 20K customers over the past 12 months. We have this burger joint bonanza restaurant. We have demographics, we have burger types, we have revenue. And for the burger types, we have the revenue coming from each of those burgers and gender, age group, customer ID. Feel free to come here to this PDF whenever you want. It will provide clarity in case that you have any questions regarding the data. Let me close it and hopefully let me try to see where it is, our Excel file. And here you go. Let me click on Enable Editing and let me go here to the data. We have several different tabs. We have a tab for each of the exercises that we will do. And when it comes to the data, let me zoom out here for a bit where you can see the customer ID. Let me enable content and let me get rid of this. So we maximize the amount of stuff that we see. Customer ID, age group, gender, then the revenue per type of burger, blank if nothing is coming from that type of burger. And in the end, we have revenue, which is basically a sum of all the revenues from the several burger types. For this video, I'm going to focus just on the revenue. One thing that I always like to do is to do a histogram of the data. So histograms and scatter plots, those are the ones that I use the most to get to know my data, to really become one with it. And let me select column L, go to insert and then histogram. And let me insert it here. It's always easy to start the charts in the tab itself. And then what I do is Control X, because I'm going to get rid of it here, go to the mean, and then Control V. You can also change here the chart title. So go here and put histogram of revenue. You can customize a lot of things here. But in general, just this first view already provides a good enough information. We can see that the data is definitely skewed here. Most of the data points are here on the left, while we have quite a few outliers here on the right. This would be one of those KPIs, and this is actually true for all of the KPIs that we have, but this will be one of those KPIs where potentially the median provides better insights into the typical value of the data set instead of the mean. That being said, my goal is to show you how to compute the mean. So average, and after you select average, you can actually just go here to the data and go all the way to the right, select column L, and you can select everything. It will ignore the blanks, and you'd get here the revenue average. So 57.7, this is the typical value according to the mean. One thing that you can also do, let me just briefly show you how to do a pivot table in case that you don't know how to. I need to get some data here. So let me go to our data, and from the customer ID, we can pick that to the column L and then select everything. And I did this with Control Shift. So if I go here, if I do Control Shift right arrow and then Control Shift bottom arrow, I kind of select everything. Otherwise, you can also introduce manually data, and then from A1 to L, 20,001. Now, let me click OK. This is going to introduce this pivot table in the mean tab. And here you go. We have it here. Now, I'm just going to very quickly show you how to do one so that we also have better insights. I like to put two demographics, so age group in rows and gender in columns. There's two benefits to this. So first, I have this kind of matrix-like for a KPI, and at the same time, I see the unique values. And I see that, for instance, for gender, we have male, female, and then we have this unknown, right? So people that may have omitted this question or did not answer. And then for the years, we also have a not specified as well. So this is important. Now let's go and add here revenue. And you see that we have sum of revenue. May not be super interesting, but first, before I get to it, let me organize here. So I like to format my numbers so that we have a bit of less noise here. So this is the total revenue for each of these buckets. Now, let me go here to show field list. Instead of revenue, let me show you that you can get the count, the average. Count and average are usually very good for this type of pivot table, but let me focus here on the average. Now, we would have here, so the average, then you have a grand total. One thing that I like to do here, just select everything, go to home, conditional formatting, and either data bars or color scales. They usually work quite well. Big fan of colors so that I can see what is high and what is low. And I would see that 60 years male, they provide the most revenue. And if you look at not specified for not specified in terms of gender and age, those are the ones that provide the least amount of revenue, which makes sense, right? So if you have the least information, these are customers that are not so engaged with your company, and therefore it is likely that you know the least of them. Now, this is it. So we saw how to do this histogram very quickly. We saw how to compute the average for revenue, and we did a very quick pivot table. Let's keep it going. Until the next video, have fun. Hey everyone, time to introduce you to another statistical concept, the median, which is the center of an ordered set, also called the 50th percentile. If you imagine a data set with everyone's age and you put in ascending or descending order, the middle point here would be the median. Remember our example where Elon Musk crashed our party, raising the group's average income to 1 billion? Well, it did not raise the median. Before he joined, the median was 100K, since everyone made 100K, and thus the 50th percentile was still 100K. When he arrived, the 100K continued to be the 50th percentile of the data. As a conclusion, we can say that the median is robust to outliers and skewed data. Now, you may wonder when the data set has an even amount of points, like when Elon arrived, there's no real true center, right? But two central points. For example, if we have data points, the center is 5 and 6. In this case, you do the average among data points 5 and 6, resulting in the median. In this case, it would still be 100K. Now, let me give you another example. Consider the income of people in the United States. The average pay is $54,000. However, the median is $36,000. Now, which value do you think best represents the US people? The mean or the median? This is one clear example where the 50th percentile here represents the typical value of most people, because the mean is way too affected by the very rich, which distorts the metric, resulting in not being a typical value, not representing the true center. Hence, and to reinforce, the median is resistant to extreme values or outliers and to skewed data. Let's apply what we have learned now in Excel. Until the next video, have fun. Hey everyone, in this video I'm going to show you how to do the median. Let me kick it off by computing the mean. This we already know, so average. And let me do it for revenue and for the vegan burger. Let me start here with the revenue, just select column L, and then for the vegan burger, same thing, average, and open parentheses, go to the vegan burger, and let me find it. Okay, where is it? Here we go. Column K, close parentheses, and here we have it. Now, we saw for the revenue, right? So we did this histogram. Now, based on this distribution, right? Based on how it looks like, and knowing that you have here the mean, which is 57, 58, what do you think would be the value of the median? And I'm not asking for a specific value. I'm asking for a direction. Do you think it will be more than the mean or less than the median? Feel free to pause here and think about it. But based on this kind of distribution, you should be able to infer how does the median compare to the mean. Now, let me do it. Let me do here median. And so median, I go to my column L, which is the revenue, close parentheses, and here you go. So we have less, because the thing is that usually if you have if you have like this bell shape, the median and the mean, they are pretty similar. But if you have a lot of outliers to the right, then the mean is higher than the median, like in this case. If it was the other way around, if you had outliers but from a negative perspective, then what would happen would be that the mean would be less than the median. Now, let's go here and let me get to know the vegan burger variable. Go here and then let me insert a histogram as well so that I can get to know it a bit better. Here we have it. So let me do Control X and then go to the median, Control V, so we can have a better view. Here we go. Let me zoom out for a bit, change the title, histogram of a vegan burger. Here we go. And the way that I look at it here, of course, we still have the data a bit skewed, and therefore, and please say it with me, the median will be less than the mean, but it's not as drastic as the overall revenue, as we can see it here. So let me compute, let's confirm that the median is less than the mean. So go to data, column, I think it was K, right? Here we go. Select everything. And here we have it, 31.95. Now, I'm going to stop here. As you can see, doing most of this stuff is very easy, and it will continue to be very easy throughout this section. But there's a lot more for us to learn. And really, the most important thing is that you see where to use them, what are the downsides, and really start to understand how this data and statistics come together. Until the next video, have fun. There is a third least known statistical body to the median and the mean, which is the mode, and it is defined as the most common element in a set. And we often use it for discrete and categorical variables. The simplest way of looking at it is an election. The candidate with the most votes as the winner is the mode of the election. Theoretically speaking, we can also have two candidates with the same amount of votes, and therefore we would also have two different modes here. Now, of course, that wouldn't work out in practice, and the election would be repeated, but for the sake of visualizing what the mode is, it is indeed something that is most used, most counted, most elected. Another interesting example comes from the fashion industry. It is common to see the most in-use styles or the colors or patterns of the season, which are the mode, given that it is what most people use. The thing is that the fashion is really nothing but a synonym for mode. And you can definitely say that fashion is nothing but a statistical term. Now, to finish stealing all the thunder from fashion, the thing is that fashion really stole all the excellent terms from statistics, like tendency or trend. All of these come and are widely used terms in statistics all the time. To wrap up, and before we go to our exercise, the mode is the most common element in a set or group. Until the next video, have fun. Welcome back. Let me show you how to compute the mode. If you look here at revenue, and if we go to our histogram that we have in the mean tab, we should kind of expect that the median is around here. Not super easy to see, but let's say between 22 and 30, yeah, maybe between 20 and 35, something around here. And therefore, this is what is kind of expected. So let's have a look. Let's go to mode. And again, very simple. So we just go to mode and go to revenue and close parentheses. And this would be it. Now, I'm getting an error. So what happens is that, for some reason, when I do the mode and I just select the whole column, it is giving me an error. So I'm actually glad that I forgot about this, and I'm actually showing it to you so that you'll see that my Excel will indeed crash, which, happens from time to time. Everyone that has worked with Excel knows the limitations and how it is a program that it can crash. So here we go, not responding, also not an issue. Let me try to close it, see if I can repair. Let me restart the program so that we can keep on going, and just keeping in mind that to do the mode, sometimes it's helpful just to select the part that you want to do. Personally, I really like when I can just select the whole column and it kind of does what I want it to do, but that is fine. And alrighty, so it is back. Everything seems to be here, so not really an issue. It is version 1 because it's auto-recovered. What I usually do is that I just do save as and then browse, go to the place, because it's usually auto-recovered and it is often in the cloud. and I like to bring it back. You can see that I have a bunch of videos here. So statistics with Excel and key statistical concepts, and I'm just going to save it over the burger joint Excel workbook. And yes, so here we go, replaced. We can go back now. Okay, so mode and open parenthesis and revenue. Let me go here. So Control Shift bottom arrow and enter, and okay, it works. So 29.99. This is the mode. And one thing that I shared with you is that if you look here at the revenue, and let me actually get rid of this for now, because I want to show you how to do it. If you look at the revenue, it is a continuous variable. And one thing I shared was the mode, maybe it's not really the most interesting KPI when the data is so skewed, and particularly when it is continuous, because you just may happen to get a mode that does not really make a lot of sense, or at the same time does not really represent the data so well. But what it does represent is, for instance, for age group, gender, anything that's discrete, that's categorical, it's really good. So we can do for age group here, and I'm going to show you how it does not work. So go to mode, data, and then I'm going to go here to age group, close parenthesis, and oops, before I make the same mistake again, let me select the age group, Control Shift arrow, and here you go. So we have NA. And the issue is that this mode function that we're using from Excel only works for continuous or numerical variables. Therefore, we need to find a workaround. And this is what I want to show you here as well. So what I will do is that I will go to Google, because my goal here is really not to just show you how easy it is, but also when stuff gets tough, I want to be able to show you that you can find workarounds and that you can find solution. So I'm just going to go here, type, so Excel, and you can see that I have already searched for this. So compute mode from categorical variables. This should work. And let me try. So how to find the mode or modal value. And okay, so let me start with the first one. I think I've seen this one doesn't work so well, but let me get a few more links. And okay, so they are all about the mode from, let me go with discrete variables instead, so that maybe I get something else. Calculation of mode in discrete series. Let me start with this one. So how to find the mode or modal value. And here we go. Let me browse. And there's nothing that really seems like some kind of categorical or Excel function for that. So let me continue. So not really working. It's all about numbers. Okay, doesn't matter. Let me close this one. Let me try with the other one. And here you go. So again, what I'm searching for would be some kind of Excel function. By the way, you can definitely use ChatGPT for this. I might just jump there because, okay, let me go. So chat, OpenAI, let me just go there. Big fan of it. And I even have the 4. So I'm a Plus subscriber. And so I'm going to go here. So give me the Excel function to compute the mode for categorical variables. Let's see what pops up. Now, let me pause here and while it runs. Alrighty, so it's done. So to compute the mode for categorical variables, you can use the mode SNGL. If your data is numeric, or the mode.mold if your data is non-numeric. I didn't know about this one. Okay, let me scratch that it was more complex. Let me actually go back and try this one. So equals mode.mold. Let me try it. We go to data. We go here, just selecting that part. NA. Okay, let me try the other one. SNLG. And here you go. Okay, also does not work. Okay, so our lovely chat GPT was wrong about it. Let me try to get it. Okay, I should have continued. However, for categorical data that is non-numeric, Excel does not have a built-in function. Okay, so my previous knowledge was correct. So a common workaround is to use a combination of all the Excel functions to determine the mode of categorical data. Here's the step-by-step method using COUNTIF and max. So let's do it, and let's do it step by step. Previously, I've done it differently, but let me just go with it and see what we can do. So list unique categories. So this we can do. Count occurrences using COUNTIF. I actually had planned this already, but with a different purpose. Find the maximum and then identify the mode. So let's do step 1 and step 2 because these I had already planned. Let me try to find our Excel. So I wanted to show you that you can quickly compute the mode using this first unique. So what you do is that you go here to the data, and then basically you get all of the unique values. And then what you can do is do this count if, and what happens is that you include a range and a criteria. So the range is the range that you want to count, and the criteria is what is it that you want to count. So this, and then comma, and then let me put here our unique value. Let me close this and let me drag it. And based on this, we would see that not specified is the most common age group. Now, what ChatGPT is then telling us, and let me go here. So find the maximum count, use the max function to find the highest count value calculated. So this we kind of done, but you kind of need to do this. So let me give it a try. So I copy this function and can also have a look here. So let me go here, select everything, Control V. So unique categories range. So this is our E2 to E8. Match max counts range. Okay. So we just select this and we take this counts range and then we do it again. We click on enter and here we go. It actually worked. So just repeat this. Please pause here in case that you did not get the same answer from ChatGPT. Feel free to copy. But what is happening is that we're basically going to apply this match function and finding the actual values and then doing the index. One thing that I actually now also want to do. So let me start here. So let me select the match so that, so Control V. So I want to show you first what the match does. So let me click on match and okay, I think I have something clicked that I should not have. So equals here. And this is initially what is happening, right? So we're going to have a look here and we're trying to find the biggest row, right? So what is the biggest value and where is it? And it's telling us that it's on row number 2. And then what the index does is, okay, you know what? In this list here that we provided, number 2 corresponds to what? In this case, not specified. And this is the outcome. I hope this is somewhat clear. Feel free to play around with these functions. And otherwise, I'll see you in the next video. Before I get to it, a challenge. So I prepared here a few questions for you to give it a try. Number one, pick a variable that would be appropriate, or at least as appropriate as it seems for the mean. Do a histogram, compute the mean. Number two, pick a variable that would be the most appropriate for the median, then the mean, right? And then do a histogram, compute, and okay, let me actually align it here to the left. Compute the mean and the median. And then last but not least, I want to know if there's more men, women, or non-identified gender customers. I'm gonna stop now. See you in the next video. Until then, have fun. Welcome back. I hope that this challenge wasn't too difficult. So let me kick it off here. If you have any questions still after this video, please let me know. I'm here to help. So the first one was to pick a variable that would be appropriate for the mean, to do a histogram and compute the mean. And one that I thought was a good one was the double cheeseburger. I mean, it was okay-ish, I guess. So let's do the mean, and to do it, let's do an average here, and let's go here. Let's find our double cheese, close parenthesis, and here we go. For the histogram, let me go here to double cheese, insert, and then histogram, and here we go. Now let me get this one. So Control X, and then going to the challenge tab once more. Control V. Let me decrease it a tiny bit. Let's briefly discuss it, right? So the data is slightly skewed to the left. Histogram of double cheese. So it is indeed slightly skewed, but it is okay, right? So it's not like some variables that we have seen that were completely skewed. This one is slightly skewed. And another thing that I thought would be good to highlight is that, yeah, not really skewed, but it's really dispersed. So these would be one of those KPIs where, aside from looking at the mean, it's also good to look at some measures of variability, which we still need to cover. Next would be to pick a variable that would be more appropriate for the median than the mean. I had a look, and crispy chicken sounded like the variable to go. Let me do the histogram first. So go to data, crispy chicken. Here you go. So column J, insert, and then histogram. And you can see that this one is really like horribly skewed to the left. Let me do Control V here. Let me slightly decrease it. And here you go. Let me add as a title, histogram of crispy chicken. Actually, sometimes these propositions are weird for me. And let's do the mean and the median, respectively, right? So what we should see is that the mean is much bigger than the median. So equals average, and then here we go. And okay, let me actually get rid. Okay, I need to go back. Let me go here to our data. Let me get rid here of this chart, and I can do it again. So average, and then go to crispy chicken, and here we go. And then lastly, the median. Let's do, I'm missing here an equal, right? So we always start the function with an equal, and data, go again to column J, close parenthesis, and here we go. Let me correct this, put it below, and as we can see, it's much, much higher. The last exercise was, are there more men, women, or non-identified gender customers? And what we can do, so let's do unique, right? Let's figure out first what is the number of genders that we have here. So all the way here to the left, column C, and here you go. Now go to female, male, and let me do count if. And first we select the range, so gender. And then I go back to challenge and I put female. This one here is just blanks, right? So it's blank data that we're seeing here. I'm going to drag it to male and this non-identified. Or better yet, I think I wasn't clear now. So this 0 would represent the values that would be here. Just for the sake of being clear here, let me actually rework here the unique. So let me go back to the data on the gender. So Control Shift and then bottom arrow or arrow pointing downward. So you can see that we select up until row 20,001. Let me click on enter and you see that the 0 is gone. But still, by this overview, right, we see that we still have some blanks here. But we also have that the female is the most common gender in our dataset. With this, we're done. I hope it is clear. Again, if you have any questions, really any questions, let me know. Till the next video, have fun. I think that the standard deviation has a bad reputation. It is likely you have studied it and even had to compute it by hand. However, do you really remember what it is? The standard deviation measures how dispersed a dataset is from its mean. Simple or not really? Well, let's try to give it an interpretation and meaning. Let's look at these two examples. I have created two histograms where you can see the number of occurrences on the y-axis and the number of fries, because we're relating this to our burger case study, on the x-axis. The graph on the bottom left with a series pretty spread apart will have more variability than the graph on the right, where the values are centered around a given number. The standard deviation is this KPI that represents this dispersion. And it's very important to truly grasp a variable metric or KPI. If, like we have on the left, if the values don't center around the mean, we have a high variability. And this results in a high standard deviation, which in that case actually becomes an issue for any business, because businesses always strive for lower variability. From this restaurant perspective, you want the number of fries to be similar each time. Aside from waste and inefficiency, it is terrible when a customer sees another better served than his or herself. Like in this image, like if you are the one on the right and you see someone with the fries on the left, you're like, not so lucky this time, right? Now, if we look here at the formula of the standard deviation of the population, the xi is the values, the x bar is the average, and the n is the number of observations. Please remember that the standard deviation measures the dispersion of a dataset. Therefore, what happens is that we subtract each value from its mean and we square it to have a positive value, because recall that any number squared is positive. Then we sum everything up and we divide by n. Therefore, the standard deviation, and the way that I like to see it, is kind of like this average dispersion, this average delta between any number and the mean. Now, one thing that might make you curious is that we have standard deviation of the population, and this would imply that if we are to have a sample, then the formula will be slightly different. And it is only slightly. The only thing is that in the denominator, the expression is n minus 1. So if we pair both equations here, we see how similar they are, right? So yn minus 1, we know that the variability of the population is less than of the sample, and this kind of serves as something that is correcting for that difference. That being said, when we have enough observations, like in our case study, this doesn't really make a difference. To sum it up, the standard deviation measures the dispersion of a dataset and its variability. Businesses usually strive for low variability and thus few defects. Most often, people search for consistency in quality. So if you are to imagine a product that is consistently 4 stars out of 5 and another that is sometimes 3 stars and sometimes 5 stars, which one would you really prefer, right? So consistency, right? People assign consistency to quality as well. Finally, there is another word that it's important for you to know. So the variance, which is nothing but the standard deviation squared. That is absolutely it. It is the same thing, but in different magnitudes. One, you use the square root, and the other, you do not. So if someone says standard deviation or variance, they are talking about the same thing because the meaning of the KPIs is absolutely the same. Let's apply this. Until the next video, have fun. Welcome back. In this video, we are going to do the standard deviation. I always like to look at the standard deviation while also looking at the mean at the same time. And that is because these two go well together, right? Because I don't know if you can recall, but in the formula for the equation for the standard deviation, we do the delta between the values of x and the average, right? So this implies that the average is an important element for the computation. Let me go, so column L for revenue, and then let me find the one for double bacon and double bacon. Here we go, column I. Now for the standard deviation, if you recall as well, there's two formulas, right? So one for the sample and the other one for the population. So for the sample is stdev.s, and let's get it. And let me go here to revenue. That would be column L. Here we go. And let me add here. So standard deviation sample. And here we go. And then let's also do the standard deviation of the population. Here we go. And okay, let me format this the same way so that we have a clearer view here. And it is stdev and then dot p for population. And just go here and do column L just for the sake of repeating this for double bacon. So stdev dot sample. And as soon as we wrap up this functions part, I would like to walk you through some of the key conclusions for me. So stdev dot population, and then let me get the double bacon, and here we go. So what are the things that I want to share with you? So first one, as rule of thumb, right? We consider data to be dispersed if the mean, or better yet, if the standard deviation is bigger than the mean. This is a rule of thumb, right? So it doesn't mean that, it's always true. It's like, let's start there and start to make some categorizations. And the most importantly, right? So I share with you that there's two different formulas. And the thing is that, as you see, like the outcome is almost the same, right? So here we have slightly bit different. And what I want to share with you is that often than not, you can cut corners in statistics, right? You won't be theoretically correct, but you'll be practically correct. And when it comes to the application, that's the most important thing, right? So don't be concerned that you're not considering everything. Most of the times when it's like this tiny little thing that changes, it doesn't really matter. Those were the two things that I want to share with you. My rule of thumb, which is a general rule of thumb, and this one, especially when you have two different formulas that are almost the same, the results are also almost the same. Let's continue, and until next video, have fun. In this video, I'm going to cover one of the most important metrics used in statistics, which is the coefficient of variation, also known as CV. If we are to define it, we would say that it is a measure of the relative variability of a set of data, and it's usually expressed as a percentage of the mean. In simple terms, it's the ratio of the standard deviation to the mean, multiplied by 100. This metric provides a standardized way of comparing the variability of different datasets, regardless of their mean values. Now, let's see how CV works with two real-world examples. Example number 1, so stock market returns. Suppose that you have two stocks, stock A and stock B. Stock A has a mean return of 10% with a standard deviation of 4%, while stock B has a mean return of 5% with a standard deviation of 2%. Now, which of these would be more volatile? We would use here the coefficient of variation. So for stock A, we would have 40%, so 4 divided by 10 multiplied by 100, and it would be the same for stock B, 2 divided by 5 times 100. So as we can see, both stocks have the same coefficient of variation, meaning that their variability is the same relative to their mean returns. So what does this mean exactly? An investor has to brace themselves for similar ups and downs, regardless of the mean return, if they invest in either of the stocks. In other words, the volatility that you might expect is the same. A simpler example now related to our burger juiciness score. Again, we have two fast food chains, chain A and chain B, both serving burgers. Chain A has a mean burger juiciness score of 8, while it has a standard deviation of 1. Chain B would have a mean burger juiciness score of 7 with a standard deviation of 2. Now, which chain serves burgers with more consistent juiciness? Well, for chain A, the average would be 12.5, and for chain B, 29%. So chain A would have a lower coefficient of variation, meaning that their burger juiciness is more consistent relative to their mean compared to chain B. This means that if you are in the mood for a juicy burger, chain A is the more predictable dining experience. Now, even though we could see that one is better than the other, that's not the point here. What we're trying to see is if one is more consistent, if one is more predictable, if one has a lower relative variability. This is what is the most important for us. Therefore, and as a conclusion, the coefficient of variation is a valuable tool in data analysis because it provides this standardized way of comparing variability across different data sets. So whether you are an investor or a juicy burger aficionado, if you understand the coefficient of variation, this can help you make better and more informed decisions. Let's apply this in Excel. Until the next video, have fun. Welcome to this video, which is probably the shortest video of this section. And that is because we know how to do the average, we know how to do the standard deviation. So let me provide that for you already and just show you the coefficient of variation, which is the standard deviation divided by the mean. Now, as we look here, right, and I would recall my rule of thumb, if you have the standard deviation bigger than the mean, this would imply here that this coefficient would be more than 100%, then we would consider the data to be dispersed. And if it's less than that, then not so dispersed. That said, right, always consider that you shouldn't really compare datas, right? Always try to get to know the data, see its evolution, whether it's getting more dispersed over time or ideally from a business perspective, less volatile, right? So less dispersed over time. And this is it. So keeping it simple, until the next video, have fun. Hey everyone, in this video I'm going to talk about the normal distribution, also known as the Gaussian distribution. And I'm sorry that I need to introduce you to so many synonyms, right? So mean, average, normal distribution, Gaussian distribution. I know that this is a complex topic because, at least for me, I find it difficult when you have so many words for the same thing. It can be complex because it's like you're learning a whole new vocabulary. When it comes to the characteristics of the normal distribution, it is symmetric around the middle, and the mean is also around the middle. And this can be seen roughly by this image here on the left, and this vertical line represents the average. Now, the characteristic is that the data is mainly around the mean values, meaning that it's not very dispersed, and the shape is similar to a bell. And this is also part of the Gaussian distribution, also called a bell distribution. In real life, this is the most important, right? We do see a degree of similarity to a normal distribution in our problems. But again, the match is never really 100%, as we'll be able to see. That's point one. At the same time, it's never that far off, as we'll also be able to see. The normal distribution brought this 68, 95, and 99 rule, representing the share of observations within 1, 2, and 3 standard deviations. To illustrate, let's look at this image here, and we see that within one standard deviation, and this would be this U symbol plus the sigma. Sigma represents the standard deviation. So U plus standard deviation, U minus standard deviation, U plus 2 standard deviations, minus 2 standard deviations, and so on. So within one standard deviation, 2 and 3, there are respectively 68, 95, and 99.7% of the observations. Which may lead you to ask, okay, Diogo, great story. What's the point in all of this? It seems more like geeky trivia more than anything else. And yeah, definitely geeky trivia. But the important thing is that the normal distribution is a pattern. And what it allows us is to categorize data with greater confidence. For example, let me give you 2 sentences, right? So 3% of customers purchase above 2 standard deviations. 3% of customers purchase above 3 standard deviation. Based on the normal distribution, we can say that the first fact is within normality. However, the second deserves attention as it breaks the historical patterns. It doesn't mean that there's necessarily something wrong with it. It just means that maybe, just maybe, something weird is happening. While for the first sentence, everything seems to be okay. As one last example, and just for curiosity, have you ever heard of Six Sigma? It is a set of practices or tools for continuous improvement. The name Six Sigma actually comes from the normal distribution. It actually represents a goal within 6 sigmas or 99.99 and so on %. The goal is that each product is defect-free. Now, let's see how we can apply this to our data set. And until the next video, have fun. Welcome back. Let's go through the normal distribution. And I picked this variable specifically because it's really one of those where you should not really rely on the normal distribution. And you'll see why in a bit. So if I look here at this revenue histograms completely skewed to the left, it has this weird break around 100. And then you have quite a bit of outliers. It's really not indicated to first use the average and therefore to use the normal distribution. And because the way that you look at it, it's not a good representation of the typical values, you should use the median, for instance. And what I want to show you is that even though it's not indicated, it still kind of works. So let's go through it. We have here the observations. Let's count how many we have. So let me go data. Let me go here, column L. I'm going to count how many. So it's 20,000. Then I'm going to do within 1, 2, and 3 standard deviations. And what I'm going to do is this plus and minus. So minus here and plus in the other one. And what I'll do is, okay, mean minus 1 standard deviation plus 1 standard deviation. So let me also log them. To log, if you don't know, it's F4. So this minus, and then I will go here to this S1. Let me log here the column. So I just log the A times, and then I'm going to get the standard deviation and log it. So F4. And here you go. Let me click on enter. Now let me repeat the process, but here instead of minus would be plus. So this works. And then here lastly it would be share of observations. Let's compute it now. So what I want to do, and let me start. So count ifs. And then here you go. So criteria range 1. So let me get here the revenue, comma, and my criteria number 1 would be when it is more than the value of the mean minus the standard deviation. And the way to do it is that you put here the quotes bigger than, close quotes, and then you add an and. Let's go back to our tab and let me do here and select. So this is 1. And you can see that it's kind of working. Let me divide this by the number of observations. Let me log it as well. Here we go. We have that 86% of the observations are higher than 23, right? But the rule is more than 23 and less than 92. So let's add this second part. So comma, you go to the data, you get our L column, and then you do comma, criteria number 2. So it's the opposite. So you do comma, less than, comma, or better yet. So you do quotes, less than quotes, and then you go back to the normal distribution. Go here to cell C6, and we get 72%. So even though it's not indicated, I would recall that the value that we should expect under a normal distribution would be 68. It's still not that far off, right? 72 is like, you would expect that something is not indicated to be completely off. Now, let's get our standard deviations here, compute for the remaining. We have negative values, which for us does not really make sense because we talk about revenue, and revenue is always positive, but still, right? Not indicated per the chart, not indicated because these values don't make sense. And still we have 96, pretty close to 95, and 99%. So you can see that especially for the tier 2 and 3, for 2 and 3 standard deviations, it gets really close. So even though it's not supposed to be, like, you can kind of still rely on it, even if it's just for a way to look at it and make an initial inspection. Now, what is the percentile of a customer with 80 euros in revenue? And I'm going to show you using the normal distribution. This is the quick way. And the count if, this is the way when you have the data, right? So this is going to give you based on the data that you have. The normal distribution is going to give you based on distribution, right? It's rather, okay, so if I know my standard deviation, if I know my mean, I kind of can do everything. And this is something that you can do. But let's start with the count if. So let's go here to the range. And I want basically when it's less than, and then and 80. Let me close. And here you go. Now let me divide this by the number of observations. Here you go, 77. So we know that we are in the top 23 percentile, or that customer that spends 80 euros spends more than 77% of the people. And then using the normal distribution, it's called norm.dist. So this is the function that you can use. There's 4 things that you can include here. X means standard deviation cumulative. So X is easy, right? So it's our 80. The mean we also know. The standard deviation we also know. And what we're lacking is this cumulative. And this probability. So this is the probability of someone spending exactly 80 euros, which is not really the question. The question is, what is the percentile? And this relies on a cumulative distribution function, because we're going to see all the customers that spend up until 80 euros. This is the part where the cumulative comes to be. Let me put true, and then we see 74%. So again, answering this question, we see that based on our data, we know the data, we see that 77% or percentile. And if we were to use the rule, it wouldn't be that far off. Hope you enjoyed this. I hope you also see that even though it's flawed, even though you cannot apply it all the time, you can still kind of do it. Again, theoretically, not really, but in practical terms, you can actually manage to get at least first results. Till the next video, have fun. In this video, we're going to talk about covariance. Now, the name is slightly connected to a concept that we have seen. The variance measures the dispersion of a dataset. The higher it is, the more dispersed it is. The covariance indicates the direction of the linear relationship between two variables. Another way to look at it is that it measures the joint variability of two variables. If the covariance is bigger than 0, then the linear relationship is positive. When one goes up, so does the other. An example can be seen by this image on the right. If the covariance is less than 0, then the relationship is negative. When x is high, we expect y to be low, and vice versa. When the covariance is close to 0, the relationship does not really exist. For example, let's say that you are studying the heights and weights of a group of people. If you calculate the covariance of the heights and weights, you might find that people who are taller tend also to be heavier. And in this case, the height and weight of variables would have a positive covariance. On the other hand, if you're studying the number of hours of sleep and the number of hours of exercise for a group of people, you might find that people who sleep more tend to exercise less. And in this case, sleep and exercise variables would have a negative covariance. Now let's look at the formula. On the numerator, we have the product of the deltas between the x values and the average of x by the delta between the y values and the average of y. And we have this product and we sum the product. And then we divide by n. Another way, or the way that I like to have a look here or to interpret, is that the covariance provides this average delta of the variance of two variables. In other words, what we're seeing here is that if two variables have a very high joint relationship, they would have a very high covariance. And this would only happen if both x, or if the deltas of x and by the x average and the y by the y average, if they have the same sign. So when it happens that they're both positive or both negative, because if one is positive and the other one is negative, they kind of annul themselves, and that would imply low covariance. On the other hand, as you can see here, we have covariance of the population. This would also imply that there's a covariance of the sample, and this would mean n minus 1. Finally, and if you are to take one thing from this video, it's this slide here. The covariance only measures the direction and not really the strength, because if we look here at the formulas, we don't really have something to say that a high covariance or a low covariance implies strength or any kind of that. We actually need another KPI, which is the correlation that we still need to learn about. So this is the one key idea for this slide. Now let's see how this actually works in Excel. And until the next video, have fun. Hey everyone, another short video here just to show you how to do the covariance. It's not really a KPI that we use. I have it here because it's helpful to introduce correlation and the relevance of correlation, because in general, the correlation is like the covariance, but better, because covariance introduces us the direction in which two variables go together. So it's either negative, positive, or not at all. And the correlation not only does that, but adds the strength. But again, I'm kind of spoiling the next video. Let me show you here covariance. And here you go. As before, we have of the population of the sample. We always use the sample, but we have in mind that it's very, very similar. So first one is the cheeseburger and the bacon burger. I think I got it correct, right? So bacon and cheeseburger. So covariance is 32. The other one would be cheeseburger and double cheese. So covariance again of the sample, and let me go here. Let me get the cheeseburger, comma. So not an M, but rather a comma. And double cheese. So column H. Close parenthesis. And we get the covariance of 93. Now, if we are just to look at it, right? Yeah. So positive relationship. This one is for sure. But it's a bit difficult to make any inference from here. And this is why we need to cover the next KPI. Until the next video, have fun. Hey everyone, I will introduce you now to the concept of correlation, which is one of the most used statistical concepts in the world. Similar to the mean, there are multiple types of correlations. We'll focus on the Pearson correlation, which is the most common. The correlation measures the strength of a relationship between two variables. Let's imagine that we have these axes with two series that intertwine. The correlation will measure whether both series move in the same direction. If they do, they have a positive relationship, and otherwise they do not. The value of the correlation metric varies between -1 and 1. If the value is 1, the relationship is positively strong. A simple example of a robust positive relationship would be people using umbrellas and raining. If, on the other hand, it is -1, it is negatively strong. And an example of a robust negative relationship would be umbrellas and a sunny day. Lastly, if the correlation is 0, then it means that we don't really have a relationship between two variables. And an example would be eating chocolate and swimming in the pool, since there's not really any connection between both, even though that sounds absolutely amazing and disgusting. Now let's look at the formula. It can be quite complex. The most important thing is that on the numerator, what you have there is the covariance part, right? And what you have below, this delta, again, between xi and x average, yi and y average, this is what makes the common denominator. And this is what will make this vary between 1 and -1. And the most important thing that I want to take from here is that the correlation is telling us the strength of the relationship, and I'll show you how easy it is to compute. Now let's focus furthermore on application. So correlation is at the heart of machine learning. A simple definition of machine learning is the use of algorithms and statistical models to figure out patterns in the data, learning and adapting to each problem over time. It's a complex topic, but its basis is topics like correlation and standard deviation. And let me give you one actual example. So Netflix recommendations, the movie that you get recommended to watch next is based on your previous watching historical and whether people with similar history as yours have watched and liked the movie. In straightforward but very accurate terms, correlation can be described as me saying to you, you like ice cream and I also like ice cream. I think cake is really good, so maybe you'll also like cake. The last part, and I honestly think that this is the most important, is that correlation does not imply causation. Just because there's a strong relationship between two variables, it does not mean one causes the other. And to wrap up this video, let me show you some funny, spurious correlation. Gonna go here to Google, gonna write spurious correlation. This is something that I like to show. And I like this website here. And let me show you some. So per capita cheese consumption correlates with number of people who died by becoming tangled in their bed sheets. Divorce rate in Maine correlates with per capita consumption of margarine. Age of Miss America correlates with murders by steam, hot vapors, and hot objects. And this website is absolutely filled with these kind of relationships that showcase that even though two things might happen to be connected, it doesn't mean that one causes the other. And please really have that in mind as you apply a correlation. Let me show you now how this works in Excel. Until next video, Have fun. Welcome back. Let's do the correlation between bacon and a cheeseburger. Let me correct this one. And cheeseburger and double cheese. And here you go. So to do it, it's super simple. So corral, and then we go to our data. We do cheeseburger and bacon burger. And actually, I cannot really select like this. Let me do it differently. So column D, comma, and then column E. Close parenthesis, and here you go. Let me just repeat the process for cheeseburger and double cheese. So cheeseburger, comma, and then double cheese, comma, and here you go. Now, two things I want to share with you. So first, what would be considered to be a low or a weak relationship. I think this is a better way to put it. Weak relationship, medium relationship, and a strong relationship. So how does this work? So a weak relationship is something that is more than 0.1 of correlation. So in this case, our bacon cheeseburger has basically a no relationship. And our cheeseburger and double cheese would have a weak relationship. After 0.3, it becomes a medium relationship. And after 0.5, it becomes a strong relationship. Again, these are rule of thumbs. As you get to know your data, as you start to have a better overview of the KPIs that you're overseeing, this becomes a clearer way of putting it, right? So kind of go away from these rule of thumbs that I'm sharing with you and really tailor these to the problems at hand. The last thing I want to share is I want to do another type of plot for bacon and cheeseburger. And what I would like you to think before I do it is what could it actually look like? So if I were to do it, and I'm going to do it, right, how would it look like for something that has a correlation of 0.06? So let me do it. And so bacon and cheeseburger. So it's these two. So column D and E. Let me try to select everything. So insert and then a scatter plot. So here we have it. And let me bring it here. And okay, let me zoom out for a bit because it's too big. And let me just change the title while you can also have a view here. So scatter plot of bacon and cheeseburger. Now, what kind of relationship is this? It's really no relationship because cannot really define a pattern with the exception that there is no pattern. It's not going up, it's not going down. It's not linear, it's not non-linear. It's really nothing. And this is what then results in that the correlation is 0.06, close to 0, because there is no relationship. And this is what I want to cover, right? Sometimes we see charts, but the charts are related to metrics. And sometimes we have metrics and we can kind of imagine how they look like in charts. Till the next video, have fun. Welcome to the revolutionary world of the Houston Rockets under the leadership of General Manager Daryl Morey and Head Coach Mike D'Antoni. This team transformed from traditional play to a data-driven powerhouse, where statistics and analytics became the core of every decision, from gameplay to player acquisition. Central to the Rockets' strategy was a radical shift in shot selection, pioneered by Morey's analytical approach. The team's statistical analysis revealed that mid-range shots were inefficient. Consequently, they pivoted to prioritize three-pointers and layups. Key players like James Harden exemplify this strategy, often leading the league in three-point attempts and driving layups. This shift not only increased the Rockets' scoring efficiency, but also sparked a league-wide trend, significantly increasing the average three-point attempts per game across the NBA. The Rockets' recruitment approach was also a game changer, marked by their strategic use of advanced analytics. They leaned heavily on metrics such as player efficiency rating, a statistic that summarized a player's overall impact on the game per minute. This was crucial in scouting players who, while perhaps not headline makers, were highly efficient and synergistic with the Rockets' system. Additionally, they utilize metrics like true shooting percentage and win shares to evaluate a player's scoring efficiency and overall contribution to the team's victories, respectively. This approach led to significant acquisitions and development of players like Clint Capella, who thrived in the Rockets' style of play. Their focus and statistical synergy over individual star power redefined team dynamics and proved successful in building a competitive roster. The results of the Rockets' data-centric approach were unmistakable. So under Amori and D'Antoni, the team consistently achieved high regular season standings and made deep playoff runs, challenging traditional powerhouses. Their offensive efficiency, measured by points per possession, consistently ranked among the top in the league. This success was a clear testament to the effectiveness of their analytics-driven approach. Over the course of several NBA seasons, particularly from the mid-2010s onward, the effectiveness and sustainability of the Houston Rockets' analytics-driven strategy became increasingly evident. Their approach notably influenced the league's overall playstyle. For example, the Golden State Warriors, under coach Steve Kerr, embraced a similar focus on three-point shooting, which played a significant role in their NBA championships in the 2014s, 2015s, 2016, 2017s, and 2017-2018 seasons. Additionally, the Philadelphia 76ers adoption of a data-centric strategy known as the process, initiated in the 2010s under general manager Sam Hickey, set the stage for their playoff appearances in subsequent years, including reaching the Eastern Conference semifinals in 2018 and 2019 seasons. Other NBA teams began to adopt similar strategies, shifting the overall style of play towards a more analytics-focused approach. The Rockets, through their innovative use of sports analytics, changed not just their own trajectory, but also the landscape of basketball. Welcome to the fun and interactive section on confidence intervals. Are you ready to dive into the world of standard error of the sample mean, z-scores, and confidence levels? I've got everything you need to master these concepts, including Excel tutorials, quizzes, and even a case study on Guinness beer and the t-distribution. First up, we'll start with the standard error of the sample mean and learn how to calculate it with Excel. Then we'll test our knowledge with a quick quiz. Next, we'll move to the z-scores and standardization. And again, we'll use Excel to help us understand the concepts better, followed by a quiz. We'll also learn about the confidence level, and I am sure you can see where I'm going. Lots of practice activities, lots of concepts, and even more practice activities. So get ready, and until next video, have fun. Hey there, pizza lovers. Are you ready to learn confidence intervals while chowing down some delicious virtual slices? Well, I know I am. I've been in a major pizza phase lately, so I came up with this awesome case study featuring an imaginary pizza joint called Diogenes. We'll be looking at the sales and other key performance indicators for 1 month, and let me tell you, it's going to be cheesy, saucy, good time. But before we dive into the numbers, I want to know where your loyalties lie. What is your favorite pizza restaurant? Leave it in the comments. Trust me, it will be a fun distraction from all the statistics talk. Now, let's talk Diogenes. They're famous for their decadent filled crusts, and it's no surprise that most customers opt to add extras like cheese or pepperoni, even if it means paying a little extra. For the KPIs that we have, of course, we have the price that people paid and the delivery time, and of course, the delivery would be free for the customers. So let's learn some statistics with pizza. Until next time, have fun. Hey everyone, I am about to show you a very common concept in statistics that can also be confusing because of its name, which is the standard error of the sample mean. Now you could ask, Diogo, didn't we already do this standard deviation? Isn't it the same? Why? And if yes, then isn't it just the same except for some ridiculous technicality that someone invented 70 years ago? Well, believe me, it's not, and we'll cover that in this video. However, I can assure you that I'm really trying to save you on the technicalities and just focusing on the practical applications and what we actually need to know. The standard error of the sample mean, which I'll abbreviate to just standard error, is crucial for calculating the confidence interval. From a definition perspective, it estimates how far the sample mean is likely to be from the population mean. The formula does indeed use the standard deviation as the starting point, but then it divides it by the square root of the number of observations. Now, let's really focus on the practical implications. If we compare now the definition of standard deviation, which is the degree to which individuals within the sample differ from the mean. Hence, whereas the standard deviation measures how much the observations differ from the mean, the standard error compares the sample means versus the population's mean. So, similar, but very, very different. Standard deviation focuses on individual observations and focuses on the average dispersion. The standard error of the sample mean focuses on comparing the sample's mean versus the population's mean. And that is it, I promise. Until the next video, have fun. Let's kick off our practice activity. Please come to the folder that I've shared with you, Statistics with Excel, and then to the confidence intervals folder. Click on Diogenes Pizza Restaurant and let's kick it off. First, let me zoom in and let me show you what we have as data. Here we go. So pizza restaurant, we have for each order, it's basically one pizza for simplification here. We have the product name, so pepperoni, Hawaiian, calzone, and so on. We have the crust, which is the thing that Diogenes Pizza Restaurant is famous for. Then we'll have the number of toppings, the price, the delivery time, and the number of pizzas the customer ordered before. So very simple data set, but I think it's really cool. Let's go with our first practice activity, which is to compute the standard error of the sample mean. We also have here some instructions as well. So we want to compute the standard error of the sample mean for price. And I would recall standard error of the sample mean compares the sample's mean and how likely it is to be different from the population mean. So let's kick it off and let's do our first KPI, which is the mean, which you already know how to do. So we come here and we do, for instance, the average, open parenthesis, we go to our data and we get the price. Close parenthesis, and here we go. Now, for the standard error of the sample mean, standard error, what do we need? We need the standard deviation, and we need as well the number of observations. Here we go. And it's very, very simple. So standard deviation, we already know. So STD. Now we have a sample, right? Because we are computing the standard error of the sample mean. We have a sample. So this makes it easier for us to figure out which standard deviation function to pick. Let's go get it. So price, close parenthesis, enter, and here we go. How many observations? So we do count, and then open parenthesis, and then we go to price, close parenthesis, and here we go. Now, the standard error is the standard deviation divided by the square root, SQRT, of the number of observations, so n. And here you go. Let me close parenthesis and do enter. Now, how to interpret this? Given that our mean is 19.3, and given the number of observations that we have, the standard deviation, it is very likely that the true population mean is between 19.2 and 19.4. So 19.3 plus or minus 1. And this is how to interpret this. I have to say two things now. So the first one is that you don't usually just compute the standard error of the sample mean. This is something that it's a building block for the confidence intervals. That's one very important thing. Moreover, I don't want you to memorize formulas. And this is why I'm also building this. Unfortunately, Excel does not have a formula for standard error of the sample mean. So we need to compute it ourselves. However, I'm just going to highlight here in light yellow so that you just need to change this. And I'm also going to leave this one here on the right so that it has a formula. This is something that you don't really need to change. When you are to apply this in your career, in your job, this is where the templates make sense. Because it's not really reasonable for you to memorize formulas. It does not make sense, but you can use templates. And I think that's really cool. This is it. Until the next video, have fun. Welcome back. In this video, I'll talk about the standardization score, also known as the Z-score. The key idea is that it provides an estimation of how far away is a data point from its mean. Another way to look at it is that the Z-score compares the observation values to a normal distribution. If you look at its formula, we see that we subtract the mean under the symbol of u from the observation, and then we divide everything by the standard deviation, like super simple. For me, the goal of the Z-scores is to standardize values and to make them comparable. One real-life example is college results, which differ from country to country or test to test. In Portugal, the university results are given from 0 to 20, where 10 would be the passing grade. That is very different from the US, where the results are from A to F. Hence, to compare, we should standardize the values. My grade point average in university was 16. If we assume the average GPA was 13 and that the standard deviation was 2, then my Z-score is 1.5. Another way to interpret this is that I am 1.5 standard deviations from the mean. And yes, reducing myself to a statistic has always been my life goal. Now, let's compare to some other tests. And let me give you my GMAT score. The GMAT, for those who don't know, is a popular entry test for business schools. The grade varies between 200 and 800 for some ridiculous reason. Well, I attain 680 and the average is around 560. If we assume the standard deviation is 120, then my Z-score would be then 1. So 680 minus 560 divided by 120. Hence, in these examples, you could say that I did better in school than in this GMAT exam because the Z-score is relatively higher. So this is it. It's a simple concept and I hope you enjoyed it. Till next video, have fun. Hey everyone, let's kick off this video, and I have two tasks for us. So first one is to standardize the delivery time variable, and two, we are going to compute the share of observations below 30 minutes. For the standardization, if you recall the formula, of course you don't have to, but if you recall, we need a value, we need a mean, and we need a standard deviation. And this is what we are going to do. First, we kick off with a mean, which we already know by heart, so average, and then we get here the column A. By the way, this is the delivery time variable that we have in the data. I just put it here to make it a bit simpler. Then standard deviation of the sample, so stdev, and here we go, and let me get column A. Then I do enter, and now I kick off. And then I can start the standardization. So standardize, and we need a value, which is x, and then comma, then it requires the mean, and let's lock it. So f4, comma, and then the standard deviation, and let's lock it as well. Let's close the parentheses, and here we go. Then it's all about making it work for all of the variables. Now we have this second thing, so compute share of observations below 30 minutes. Let me put the 30 here. So one way to do it is we go here to our data, so we see here at the top, then to filter, and we can sort from largest to smallest, and we try to see here the 30 minutes in the delivery time. And here you go, so 30.02, 1.99, 29.94, 1.96. Now, with this, it would already be possible to do this, to see how many observations are within, because we have already learned the normal distribution. A simpler way is that we do this share of orders below the limit. And in here, we would just apply, because I really want to connect what we're learning now to a concept which is the normal distribution, which is very related to this. And I really want that you start also connecting everything. And when we see a problem, that you also see a solution with something that maybe you have already learned. Now, the norm dist requires x, here we go, and then the mean, and then the standard deviation, and then it is true. And let me close the parentheses, and we get 98%. That is the share of orders below the limit. Last thing I want to show you, so 30.02, 199, and then 196, and I want to show you another course material that I have for you, and it is in the material folder. In the statistics with Excel, you have this Z distribution PDF, which I will try to open. Yes, always with Google Chrome. And let me show it to you. So we have here the Z scores, so 3.9, and then this 0.00, this is the second decimal case. And have that in mind, that 1.96, 1.99 that we just saw, and we need to go through it to find it. So 1.99, let me zoom in quite a bit. And here we go. And okay, let me center this a bit. So we go to 1.9, and so this is the column, and then we need to find the 1.9. So 1.96, and then the 1.99 is this one. So this is where we get the share of observations. In case that you've forgotten how to use the norm dist function, you can also use this table here, because that would enable you, if you have a standardization score, a Z score, you can use this table to find the percentage. And this is how you can also do it. It's not hardcore, but it's definitely old school, because you'd get a table, then you try to find it. It's as far from tech as you can imagine, but it is a possibility, and it's something that you can also do. This is it, and until next video, have fun. Welcome to the video on confidence levels in statistics. In this video, we'll explore what confidence levels are, how they're used, and how to interpret them. First, let's define what a confidence level is. Confidence level is a measure of the level of certainty that a statistical conclusion is correct. It is typically expressed as a percentage, and it is represented by the Greek letter alpha. A common confidence level is 95%, which means that there is a 95% chance that the conclusion drawn from the data is correct. This means that if the same study were repeated multiple times, in 95% of the cases, the same conclusion would be reached. Now, let's look at this graph to see how it works. We have the distribution with the mean around the center. A 95% confidence level means that we have 47.5% happening here on the right and another 47.5% on the left of the mean. Consequently, from a distribution perspective, a 95% confidence level means that we go from the 2.5 percentile to the 97.5. Now, let's connect this to the normal distribution. If we look at it, we can look for the point where it is 0.975, which is 1.96. This means that the percentile 0.975 is 1.96 standard deviations away from the mean. Consequently, if we look at the 0.025, and if we have in mind that the normal distribution is symmetrical, we would have minus 1.96. Now, of course, I'm showing you this old-fashioned way of doing things, but of course, in the practical part, it will be easy with our functions. But now let's go one level deeper and let's see how they're used. They're used for hypothesis testing, which we'll see in the hypothesis testing section. And they're also used for confidence intervals, which is a range of values that is likely to contain the true value of a population parameter with a certain level of certainty. The width of a confidence interval is determined by the standard error of the sample mean and the confidence level. But don't worry about it, we'll go through this in the confidence interval lectures in more detail. The most common confidence levels used in statistics are 90%, 95%, and 99%. Let's see how they work. A 99% confidence level means that we go from the 0.5 percentile to the 99.5 percentile. You can see that we get pretty much about everything. 90% confidence level translates going from the 5th percentile to the 95th percentile. So we still get a lot, but of course the tails, this is something, or more, these extreme values is something that we don't attain as easily. In conclusion, confidence levels are a measure of the level of certainty that the statistical conclusion is correct. They are used in hypothesis testing and to calculate confidence intervals. And keep in mind that high confidence level does not necessarily mean that the results are more accurate, but rather that they are more certain. And this is the most important thing. Until the next video, have fun. Let's see how to make these confidence levels work in Excel. We have talked about the 90% confidence level, 95 and 99. And then we also know that it goes between X and Y from the percentile perspective. 99% goes from 0.005 to 0.995. 95% goes from 0.025, so 2.5%, to 0.975. And then finally, 0.9 goes from 0.5 to 0.95. The question is, so imagine that you have a confidence level and you want to see what is the z-score out of it. Of course, I've shown you the table, you know how it works. But what about Excel? Let's see how it works. We have a few functions here related to the normal distribution. And the one that you can get, or the one that you can use, is this norm s. So the norm.s.dist, we get as its score, and then it's cumulative or not. And then the other one, which is the one that we're going to use now, is this norm.s.inf, in which we just get the probability, so A2. Let me close the parentheses, and this is what we get, 2.68 negative. Now, let me copy the formula, because I tried to make this a bit prettier, but now if I drag everything, it becomes ugly. So one way, if you want to keep it pretty, is that you select everything, do right click, and then you paste just the formula. Okay, so here you go. I made a mistake, should be 0.05. And first, of course, you can see the symmetrical part here of the normal distribution. And this is actually what I just wanted to show to you. So if you have a confidence level, how much does it translate to z-score? And to reinforce just once more, this 0.95 corresponds to 1.64. What does 1.64 mean? It means that it is 1.64 standard deviations away from the mean. Now let's look at the other scenario. We have the z-score and we want the confidence level. And again, of course, we can go through the table, but let's use Excel. It is the norm.s.dist. And this is what we include. We include the z-score, and cumulative we include as true. And here we go. We get 0.05. Let me select everything, paste as a formula, and here we go. In general, this was a video not so much focused on the business analytics side of things, but rather focused more on how to make Excel work with statistics in this particular case of the confidence levels. But still, I think it will be useful for the future, as we'll be able to see. Until the next video, have fun. Let me introduce you to the crucial concept that is a confidence interval. The first thing you need to know is that the confidence interval, or this formula that I'm showing you here, is when you have a data set with more than 30 observations. I would further add that it would be best if you were to have above 100 observations. This formula here, so this is the confidence interval for an average, which is average plus or minus because it's an interval. And then we have the z value, and this is the standard error of the mean. As a result, this lecture here is a combination of what we have been learning so far in this section. And this is a very cool thing because it's now that everything comes together. Furthermore, we have discussed here above 30, above 100. If you have less than 30, I would not recommend applying statistics. The fewer data you have, the more likely it is not good to extrapolate it to something else. And this is very important, but of course, I will show you how to do it. So throughout this section, I'll show you if you have less than 30 observations, I'll show you how to compute the confidence interval. I would like to focus now on the z value, which is the desired confidence level. Based on how certain we would like to be that the parameter is within a specific interval, we would also choose an appropriate confidence level. The most common one is 95%. Now let's visualize how it actually works in a distribution if we want a 95% confidence interval. Since distributions are open-ended, usually on both sides the confidence interval goes from 2.5 to 97.5 percentile. Now, why is that important? Because to find the confidence levels, there are tables we look at. For instance, we have seen this table already. We also have it in our course materials. If we want to find the value for minus 1.96 or plus 196, we would go through the table to find it. And for instance, we would have here 0.0250 or 2.5%. And inversely, if we want to find the associated z-score value associated with 2.5%, we would do the exact opposite. We would find here the value and the associated z-score. Now, let's put this into practice. Let's go through a real-world example. And one that is really common is market research. Let's say that Apple is interested in determining the percentage of customers who are likely to purchase a new iPhone, even bigger and more premium. The company conducts a survey of a sample of customers and finds that 60% of them indicate they would purchase the new product. However, and this is the key business reason for confidence intervals, it's important to note that the survey result may not exactly be the same as the true population accuracy. So the company wants to know how accurate their survey results is. They use a confidence interval to estimate the range of possible true population percentages that the survey result could be. For example, Apple may find that with a 95% confidence interval, that the true percentage of customers would fall within this range, so 55 to 65%. Now, this information is super important for Apple because it helps them to understand the level of uncertainty associated with the result. And it would enable Apple to make informed decisions about how to proceed with the new iPhone, very big, very premium launch. Furthermore, if Apple is happy with the interval of confidence and risk, meaning that the lower range would still be good from a business perspective, they might decide to invest more in the launch and marketing campaigns. In summary, a confidence interval is important from a business perspective because it allows companies to make informed decisions based on data. By understanding the level of uncertainty associated with their predictions and identifying and quantifying potential risks and opportunities associated with the given decision. Long video, but let's put everything in practice. Until then, have fun. Let's kick it off and let me show you how to compute a confidence interval. And in this case, we are going to do the average of the price. That is going to be our focus. And we want to do it with a 99% confidence level. So what we need to have? We need to have the mean. And let's do it right away. So average. And we go to our data. We have the price. We do column D, close parentheses, and press enter. Next up, we also need the standard deviation. So let me put with a capital S, so standard deviation. And here we go. So ST dev of the sample. And here we go. So we do price, close parentheses. I would highlight that we have a sample data set. Therefore, we use the standard deviation of the sample. Furthermore, it does not make sense to use the standard deviation of the population because we're trying to see how much the sample mean is away from the population mean. So here we go. Let me put here in numbers. So this is something that we have. We also need the confidence level, and for us is 99%. Next up, we need the number of observations, and let's do it. So count, and here we go to our data, and then the price, close parentheses, and here you go. Now let's first compute the z-score. I would highlight that for the confidence interval, we need the mean. This is something that we have. We need the z-score, and we need the confidence, or better yet, and we need the standard error of the sample mean. Therefore, let's start with the z-score. Now, let's see which of the functions we need to use. So norm s dist might seem the right one, but so this one requires the z-score, and no, it's not this one. We need the norm s inf, and this is the one that we want. Because we want something with a 99% confidence level, we want it to be from the 0.5% to 99.5%. And one very simple way of doing this is 1 minus the confidence level divided by 2. And let me close the parentheses, and we get 2.58. So if I do 1 minus 99%, we get 1%. And if I do this divided by 2, now it gets 0.05. And inversely, you could also get then, so if you do then 1, or better yet, 1 minus this, then you get 0.99%, or better yet, 99.5%. That is the correct figure, just to show you the full steps. Next up, we can then compute the margin of error. So margin of error. And the way that this works, so this margin of error is what is on the right and what is on the left of the mean. And to do it, like we have a negative z-score, so let's put absolute and let's make this positive. And times, and then it is the standard deviation divided by the square root of the number of observations. Remember that I've shown it to you that in the standard error, to compute it, we divide the standard deviation by the number of observations. So I'm doing it here right away. And here I can see that I'm getting an error. So we have the absolute of B6 times B3 divided by the square root, okay, maybe I did something wrong, SQRT of the number of observations. Let's try it like this, and here we go. Our margin of error is 0.27. What does this mean? It means that we have the mean, and on the right we have plus 0.27, and on the left we have minus 0.27. Now that we have the margin of error, we can then compute. So confidence interval, and then the lower bound, and then, okay, let me write it once more. Confidence interval and upper bound. Here we go. And okay, let me put a lowercase I here, and let me increase. And then it's as simple as the mean minus the margin of error for the lower bound, and for the upper bound, mean plus the margin of error. The most important thing here is that you keep these three as formulas. So these are formulas, and you just need to replace the values here for the mean, standard deviation, confidence level, and everything will work out. So imagine that instead of 99% confidence level, I want 95. then we get a different confidence interval. And you can see here that our thing on the right, it's also working. If we were to, for instance, to have 50 observations instead, then we would also have a different confidence interval. And this is what I wanted to show to you. It's by building this, so of course making sure that you understand this. This is like really important. And then when it comes to applying it to your own job, you have this template that you can just fill out, and then it computes what you need. This is it for this video. And until next time, have fun. The Guinness Brewery is a well-known Irish brewery founded in 1979 by Arthur Guinness. It is perhaps best known for its iconic stout, which is popular all around the world. In addition to being a very good brewery, Guinness has also played a role in the history of statistics and mathematics. In the late 1800s, William Seeley Gossett, a statistician and brewer at Guinness, was interested in finding a way to accurately estimate the quality of the beer being produced at the brewery. In order to do this, Gossett needed to analyze the data on the various batches of beer being produced, but it was limited by the small sample sizes that were available. Gossett was able to overcome this challenge by developing a new statistical distribution, which he called the t-distribution. This distribution is now commonly used in statistical analysis and is known as the student's t-distribution, named after Gossett, who published his work under the pseudonym Student. The t-distribution allowed Gossett to accurately estimate the quality of the beer being produced at Guinness, even with small sample sizes. This helped the brewery to maintain a high level of quality control and ensure that its customers were consistently getting a high-quality product. The t-distribution has also had a significant impact on the field of mathematics. It has been used to solve a variety of problems, including finding confidence intervals for estimates and testing hypotheses. In summary, the Guinness Brewery played a key role in the development of the t-distribution, a statistical tool that has had a lasting impact on the fields of statistics and mathematics. The t-distribution has helped the brewery to maintain a high quality of quality control and has also been used to solve a wide range of problems in other fields. Until the next video, have fun. Hey there, let's kick it off our lecture on confidence intervals, now with small samples. Now you could ask, okay, again, confidence intervals, it's going to be fine, because we are going to learn once more what is it about. We are going to make sure that you really nail these confidence intervals, because like statistics is just fun. I mean, maybe, but I'll try to make it as much fun as possible. Let's start with the basics. Confidence interval is a range of values. It's a way of estimating the population parameter. For instance, if we're trying to estimate the average salaries of all employees in a company based on sample data. And when you talk about this small sample, we have fewer than 30 observations. Furthermore, what is important for us to know is this margin of error, which is this expected deviation based on our intended confidence level that we expect to have. So the mean may vary between x and y, between our lower bound and the upper bound. And this bound, so the delta between, for instance, the upper bound and the average, this is the margin of error. We have calculated this in Excel. So this may seem already something that you already know. Next up, what is important to know is that the smaller the sample size, the larger the margin of error, and vice versa. So if we have a bigger sample size, our margin of error will be smaller. Now, when working with these small samples, as we already know, we use a different distribution. For the largest samples, we had the Z distribution, and now we use the T distribution with smaller samples. Now that we are done with the basics, we can now go through an actual example. You are a business owner and you want to estimate the average amount spent by customers. You go and you take a small sample of 15 people. They spend an average of $15 with a corresponding standard deviation of $10. Next up, you want to compute with a 90% confidence level the average amount that the customers of the whole population they would spend. And using the T distribution, you would find that the interval is actually $45 or between $45 and $55. This kind of example is something that we'll replicate in the practice tutorial for me to show you how it works. To sum it up, as you can see, the difference between small sample and large sample is just the distribution that we use. It's important that we use this T distribution with smaller samples so that we accommodate a larger margin of error because we have a smaller sample size and thus we expect a higher variability. But this is it. I really hope that I've made it simple enough and that you see the value of it. And I'm looking forward to seeing the next video. Till then, have fun. Welcome to this video on degrees of freedom. Now, you might be thinking, wait, what? Degrees of freedom? That sounds like a party slogan. Well, you're not entirely wrong. Well, I mean, you are, but degrees of freedom are all about the freedom, but that data points have to wiggle around. In other words, it's really a data college party. In this case, it's more about how many ways they can move while still fitting certain constraints. Now, let's dive deep into this concept. Degrees of freedom is a statistical concept that refers to the number of values in a set of data that can vary independently given certain constraints. In other words, it tells us how many free variables we have when analyzing a set of data. The concept of degrees of freedom is essential for confidence intervals, hypothesis testing, statistical modeling, and understanding the behavior of certain distributions. Now, this might sound a little abstract. Let me break it down for you with an example. Imagine that you're a teacher, congratulations by the way, and you've just given a test to 5 students. You've graded their tests and you want to calculate the average score. But here's the twist. You already know that the average score is 80%. So what are the possible scores for your 5 students? The first 4 students can have any scores that they want, but the score of the 5th student will depend on the scores of the first 4. That is because the constraint, the average must be 80%, limits the number of free variables that we have. In this case, we have 4 degrees of freedom. Let me give you another example. You're hanging out with 3 friends and you know that their average age is 25. And you know that the age of your 2 friends is 24 and 26, but you don't know the third. Can you guess the age of the third friend? In this scenario, you have as 2 degrees of freedom, the ages of the first 2 friends. And the third friend's age is determined by the constraint, the average age. Now that we have a solid understanding of degrees of freedom, let's explore why the degrees of freedom in confidence intervals is equal to the sample size minus 1. Confidence intervals are an essential tool in statistics for estimating population parameters based on sample data. When calculating confidence intervals for the population mean, we often use the T distribution. The t-distribution is actually very similar to the normal distribution, but accounts for the fact that we're working with sample rather than the entire population. So why do we use n-1 degrees of freedom for confidence intervals? The answer lies in the fact that we're estimating two parameters from our sample data, the sample mean and the sample variance. The sample mean is a point estimate of the population mean. When calculating the sample mean, we sum all the values of all the data points and we divide by the sample size. The sample mean is calculated without any constraints, so it can take up any value. The sample variance is an estimate of the population variance. And what happens is that it measures the dispersion of data points around the sample mean. When calculating the sample variance, we consider the differences between each data point and the sample mean. Since the sample mean is already determined, there is a constraint on the remaining data points. This constraint is the reason we have n-1 degrees of freedom when calculating the sample variance. When constructing a confidence interval for the population mean using the t-distribution, we incorporate both the sample mean and the sample variance through the standard error. The degrees of freedom n-1 used for the t-distribution are derived from the sample variance calculation, as it's the only parameter with a constraint in the process. In summary, the degrees of freedom in confidence interval are equal to the sample size minus 1 because of the constraint imposed by the sample mean when estimating the sample variance. This concept is important to understand when constructing confidence intervals and interpreting their results. I would further add that degrees of freedom is important when you have few observations, less than 30. You can think about the degrees of freedom. More than that, when the sample starts to converge towards the population parameters, then this doesn't matter. And this is it. Until the next video, have fun. Here we go. Let's kick it off our confidence interval now with small samples. And the goal and what we'll do in this video is that we have this very tiny sample of the KPI number of pizzas the customer ordered before, and we have in our data the bigger sample. And what we'll do is that we'll compute the confidence interval for this small sample for the mean, and then repeat the process for the big sample. And the goal is to compare both. How do they actually compare? How do the margin of error differs? Let's kick it off. So mean equals, and we get here our column A. And of course, I always confuse because I started writing mean, but that doesn't work here with Excel. Then standard deviation, and we do st dev and then sample. And then let me put here, or let me close the parentheses. And then confidence level, let's just go with 95%. And then the number of observations, so count, and then column A. Now let's repeat the process for the bigger sample, so average, and then data, then column F, and then everything will kind of be about column F now. Then st dev dot sample, and then go to the data, column F. Here we go. Brilliant. Then confidence level, because we're comparing, let's keep the same. And then number of observations count, we go to our data tab, column F, and here we go. Fairly straightforward. Now, this is the inputs, so to speak. So this is when you are to apply this in your own job, this is the part that you need to change. Everything now below, this is formulas. So let's start by computing the lower or upper percentile. So here we go. You can choose either or. It's roughly the same because stuff is symmetrical here for the lower. So it would be, we start with 1 minus the confidence level divided by 2. And here we go. Let me drag it and let me add one more decimal case, so we have 2.5%. For the z-score, this we already know. So we go norm, and then s-inf, and then we just include here the probability, which is, let me add a couple of decimals, 1.96. For the t distribution, we use a different function. So we start with t, and then it's still this dot inf. So it's the same. But one thing that is different, so of course we include the probability, but we also include the degrees of freedom, which is here the number of observations. And let me add one thing to it. So degrees of freedom is the number of observations minus 1. Here we go. So you can see that the t-score and the z-score, they are slightly different. You can also see actually here that our standard deviation is apparently actually smaller in the small sample. But of course, remember that we will compute the standard error of the sample mean, where we divide everything by the square root of the number of observations of n. So it will be different there. Another thing that I would like to show you, I don't think I've done so far, it's the t distribution. Let me show, because it's in our course materials. If you go to our course materials and then click on this t distribution, you would then be here in this t table. And okay, this is too much zoom. Here we go. This is perfect. And the way that you need to do it is that you need to focus here on this cumulative probability. I think for me, this is the easiest one. You have here the one tail and two tails. I find it confusing, to be honest. I prefer to work with the cumulative probability. That is for me the easiest one. And here. So we would be looking at something like this. So the t of 975, or it would also work with a one tail because it's 1 minus that. It's 0.025. And like the Z table, this is more defined, right? So it's more specific. You look at the 50th percent, 75, 80, and so on. And after you have drilled down on the probability that you want, you go through this column and you find your corresponding degrees of freedom. In our case, it's always the number of observations minus 1. Therefore, we would look here in this column, we would find the 19, and here we would get 2.09. And of course, because we were actually looking for 0.025 in Excel, we would get this, but negative. But it's the same, because now we are going to transform it into its absolute form. So this is it. Let's go back to Excel. The next step is to compute the margin of error. The formula is the same because it is the score, either t or the z-score, times the standard deviation divided by the square root of the number of observations. Or, if you want to look at it differently, the t-score multiplied by the standard error of the sample mean. So let's do it. We need to do absolutes. I always recommend, if you need something that's positive, please add absolute just in case. Multiplied by the standard deviation divided by the square root, SQRT, of the number of observations. Here we go. And let me add here. So margin of error for the small sample is 1.11. And then for the big sample is 0.15. So you see how the margin of error decreases because of the sample size. And this is like really, really important because, of course, the value here is different, but it's really the number of observations that make a difference here in this formula. Now, for the confidence interval lower bound, you do mean minus the margin of error. And for the upper bound, you would do mean plus the margin of error. And let's drag this and let's put 2 decimal cases. And you can see that the confidence interval for the big sample is really, really tiny. And it's really different as well from the small sample. And this is in general the importance of having a bigger sample size. As a result, we are done. The most important thing here is that you need to know how this works. So it's important that you understand the logic of the margin of error, the t-score versus the z-score. But then the most important thing is these are the inputs: mean, standard deviation, confidence level, and number of observations. And if you have this, you compute everything else. Till next time, have fun. Welcome to the section on hypothesis testing. I'm so excited that you're here and ready to become a master at making educated guesses and testing them against data. In this section, I'm going to take you through a fun case study on Amazon fashion product returns. We'll use this scenario to walk through the basics of hypothesis testing and learn how to apply it to real-world solutions. But first, let's define briefly what hypothesis testing is. In very simple terms, it's a process of using data to either support or reject a claim or theory. It's like being a detective and using evidence to solve a mystery. Next, we'll cover the all-important p-value. This is the probability that our observed data would occur if the null hypothesis were true. Don't worry if that sounds a bit confusing. I'll break it down in more detail and of course give you a chance to test your understanding with a quiz. I'll also cover another concept, which is the type 1 and type 2 error, which are common pitfalls in hypothesis testing. These errors occur when we either reject a true null hypothesis or accept a false null hypothesis. As we go through the section, I'll also discuss the issue of publication bias. This happens when only studies with positive results are published, which leads to a skewed understanding of the data and the real effects. Super interesting, as we'll be able to see. Next up, I'll show you how to test your hypothesis when the variance is known and unknown using Excel as our tool. And I'll also cover specific tests such as the pair t-test and the two-sample t-test. Very important for you to know the difference between them. Finally, I'll talk about the difference between one-tailed and two-tailed tests and of course show you how you can actually do it using Excel in a very simple way. So much to cover, and this is, at least in my experience, one of the sections that can be more confusing, and this is very important that I break down everything, and I'll try to do it. If you have any questions, let me know. Otherwise, let's get started and see how we can use hypothesis testing for data analysis. Until the next video, have fun. To help kick off this section on hypothesis testing, let me share one real case study of Amazon using hypothesis testing to improve their services. Amazon, the e-commerce giant, found that a large percentage of their customer returns were due to issues with the fit of clothing items. In order to address this issue and improve the customer experience, Amazon implemented hypothesis testing processes. First, Amazon formulated a hypothesis that the fit issues were being caused by inaccurate size charts on their website. They then collected data on customer returns due to fit issues and compared it to the size charts being used. The analysis of this data showed that the size charts were indeed causing a significant number of fit issues. Based on these findings, Amazon revised its size charts to be more accurate and provided additional information to customers on how to properly measure themselves to find the best fit. This led to a decrease in the number of customer returns due to fit issues by around 10% and an improvement in customer satisfaction. Hypothesis testing is important for companies because it allows them to make data-driven decisions rather than relying on assumptions or guesses. It helps companies identify problems and find solutions, leading to improved products and services. In the case of Amazon, hypothesis testing allowed them to improve the accuracy of their size charts and reduce the number of customer returns, which ultimately leads to better customer experience. For professionals, learning how to conduct hypothesis testing is essential because it is a widely used statistical tool in many industries. It allows professionals to make evidence-based decisions and improve the products and services of their companies using data. In addition, the ability to conduct hypothesis testing is a valuable skill that is highly sought after by employers. Are you now motivated to learn hypothesis testing? Well, let's kick it off. Until the next video, have fun. Welcome to the lesson on hypothesis testing. Hypothesis testing is a statistical process that allows us to make inferences about a population based on a sample. It allows us to determine whether a relationship between two variables is statistically significant or if it's simply due to chance. Now, let me talk to you about the process. We start by formulating the null hypothesis, which is this HO, and an alternate hypothesis, which is this H1. The null hypothesis is the default assumption that there is no relationship between the variables being studied. And another way to view it is that the null hypothesis is the status quo and what we are trying to disprove. The alternate hypothesis is the opposite of the null hypothesis, stating that there is a relationship between the variables. That is, the alternate hypothesis is what we are trying to prove. For example, imagine that in the previous year, each customer spent 200 euros with your company. That is the status quo and what we're trying to disprove. Therefore, the null hypothesis would be each customer spent 200 euros or customer spending equals 200. Now, this year, things have changed. Economy is not great, competition far more aggressive, and your company did invest a lot, did try to engage. So much that it is unlikely that your customer spending is the same. Therefore, that would be your alternate hypothesis, that the customer spending is not 200 euros. You don't know which direction, but given all that you know, it's very unlikely that it has remained the same. The logic behind hypothesis testing is based on probability. We collect data and we use statistical analysis to determine the probability of obtaining our observed results if the null hypothesis is true. If the probability is low, we can reject the null hypothesis in favor of the alternate hypothesis. We'll go into more detail on this topic later in this section. This is actually worthy of having just at least one lecture on this topic. So don't worry if this seems currently vague. The important thing is the logic. Low probability, we reject the null hypothesis. Now, adding to this, it's important to note that in hypothesis testing, we can never prove the null or alternate hypothesis to be true. So we can say, no, we accept the null hypothesis. That's not the case. We either reject it or we fail to reject it. And now to really understand this even a bit better, let's use a very relatable example. So please use your movie history memory. And if you recall, in those movies or series about courts and juries, if the court decides that the person accused should be set free, the exact wording is not guilty. They don't say innocent, they say not guilty. And it's the same thing with hypothesis testing and the scientific process. Additionally, and this is very important, we need to remember that we cannot prove a negative. let's look at another example. There is a species called Australian tree lobster that was thought to be extinct by 1920. Now, to prove that a species is extinct, we need to prove that all insects are not Australian tree lobsters. It would mean going through each square inch in the world and verifying that there are no Australian tree lobsters, which is realistically impossible. So you can guess that there is no surprise that they actually found the insect in 1960. To conclude, we assume that the null hypothesis is correct by not rejecting it rather than by accepting it. To sum it up, in hypothesis testing, we have the null hypothesis and the alternate hypothesis. The null hypothesis is the status quo, and the alternate hypothesis is what we are trying to prove. Until the next video, have fun. Hey there, are you ready to learn one of the most important concepts in statistics? I'm talking about the p-value. Now, you may have heard about the p-value and it may sound a little bit intimidating, but don't worry, it's fine. It will be very simple. Well, maybe not simple, but I'm really hopeful that by the end of this video and this section overall, the p-value is a tool for you and not something that is intimidating. The p-value is a way to help us understand the likelihood that a certain result happened by chance. It's like this little helper that tells us how likely it is that our results are just a fluke, that they are coincidental, that they happened with luck. Now, here's an example. Let's say you are flipping a coin and you want to know if your coin is fair or not. You flip it 10 times and it comes up head 7 times. You might be wondering, is this coin fair or is it biased towards heads? The p-value helps us to answer that question by telling us how likely it is that we would see 7 heads in 10 flips just by chance. Another example, let's say that a new drug is being tested and you want to know if it's effective at treating a certain condition. You give a drug to a group of people and you give a placebo to another group of people. After a certain period of time, you compare the two groups to see if the people who took the drug got better at a rate that is higher than the people who took the placebo. The p-value here is a tool that helps us understand how likely it is that the difference in the results between the two groups is due to chance or not. So, as you can see, the p-value is really important as it helps us to make sense of our data and understand if our results are meaningful or not, if they are statistically significant or not. Now, there are a few misconceptions about p-values that I want to clear up. First up, some people think that the p-value of 0.05 means that there is a 95% chance that the results are true. However, it's not really what it means. All it means is that there is a 5% chance that the results we are seeing are due to chance. So this is the right interpretation. Another misconception is that a low p-value means that our results are definitely true, but that's not always the case. A low p-value just means that our results are less likely to be due to chance, but it doesn't mean that they are true. We are talking about probability of happening. It's chance results that we're talking about, and this is the most important thing. Now, let's connect the p-value to hypothesis testing. The p-value is the probability value that helps us determine the significance of a hypothesis test. Why? Because it is the probability of obtaining a statistic or a test statistic at least as extreme as the one observed, assuming that the null hypothesis is true. Therefore, the p-value is a tool that we use. It gives us the threshold whether we should reject or fail to reject the null hypothesis. And this is the most important thing. And this is what we'll put into practice very soon. A small p-value, usually less than 0.05, indicates that the observed data is unlikely to have occurred by chance. And therefore, the null hypothesis is rejected in favor of the alternate hypothesis. A p-value of greater than 0.05 suggests that the data is consistent with the null hypothesis, and the alternate hypothesis is not supported. So there you have it, the p-value in a nutshell. It is this helpful little tool that helps us understand the likelihood that our results are due to chance or not. If we have a low p-value, the null hypothesis is rejected. If we have a high p-value, our null hypothesis is supported. And remember, just because we have a low p-value, it does not confirm that our results are true. It just means that it's less likely that they happen by chance. Thank you for watching. Until the next video, have fun. Welcome to the lecture on type 1 and type 2 errors. Very excited to share one example that will hopefully make it fun, but also very digestible to understand these two concepts. Let's consider pregnancy. The normal status is that someone is not pregnant, and therefore the null hypothesis and the status quo is a person is not pregnant. First, let's talk about type 1 errors, usually under the symbol alpha, and these are also known as false positives. Now, let's go to the example. Imagine a doctor in his office when a man enters complaining about the abdominal area. Without looking, he diagnosed that he is pregnant. This is a classic type 1 error. You rejected a true null hypothesis. A man is not pregnant when it was actually false. Next, let's talk about type 2 errors, commonly represented with a beta symbol. These are also known as false negative. Let's cover the same example. Imagine the same doctor now attending a female patient who is, 4 months pregnant. She says that her pregnancy is complicated in terms of pain. Now this doctor, obviously not a very good one, tells the patient that she is not really pregnant and that the pain is coming from eating too many pizzas or whatever. This is a type 2 error. You fail to reject a false null hypothesis. Then recall, woman is not pregnant. This is the null hypothesis, and you needed to reject it, and you failed at that. So this is a type 2 error, which is a false negative. Now let's connect these examples to the confusion matrix. We have in this table 4 different outcomes: true positives, true negatives, false positives, and false negatives. Now, it's not called confusion matrix by mistake. It is confusing, and it may take you a bit of time to actually come to realize how it actually works completely. But the bottom line is that you want to maximize the true positives and the true negatives. They are in green. Green is good. This is what you want to maximize. And you want to minimize the false negatives and the false positives. Now, let's recap everything. So the first example with a man being diagnosed pregnancy is a false positive. And the second example with a woman being told that she is not pregnant when she is a false negative. Now, if we are to talk about true positives and true negatives, a true positive would be detecting that a man is not pregnant. And a true negative would be detecting that the woman is indeed, well, in this case, is not pregnant, but for the sake of avoiding a double negative, the woman is pregnant. In conclusion, in hypothesis testing, we have the type 1 error, when the null hypothesis is true and you reject it. And type 2 errors, the null hypothesis is false and you fail to reject it. And that's it really. Until next video, have fun. Hey there, have you ever heard of publication bias? It's a pretty sneaky little thing, and it can have a big impact on the research we see and hear about. Essentially, publication bias refers to the tendency for studies with positive or significant results to be more likely to be published in academic journals, while studies with null or non-significant results are often left in the dust. Let me give you one example that I'm going to call the antidepressant conundrum. Imagine you're struggling with depression and your doctor prescribes you an antidepressant. You start taking it, and after a few weeks, you notice a significant improvement in your mood. You're feeling more energized, less anxious, and overall just better. You're grateful to the little pill that changed your life. But what if I told you that the little pill that changed your life might not be as effective as you thought it was? A few years back, a study was conducted that aimed to investigate the effectiveness of antidepressants in treating depression. The study, led by Dr. Kirsch and Dr. Whitrow, reviewed all available data on antidepressant trials, both published and unpublished, and what they found was shocking. The study revealed that the majority of the trials that had been conducted on antidepressants had never been published, and of the trials that were published, most had positive results. However, when the researchers looked at all the data, including the unpublished trials, they found that the drugs were not as effective as previously thought, and that they carried an increased risk of suicide in some patients. The reason for this is that pharmaceutical companies only tend to publish trials that have positive results, and they often bury the trials that have negative results. This means that doctors and subsequently patients only see a biased view of the effectiveness and safety of these drugs. As a result, many people are taking antidepressants that may not be helping them, and some may even be putting themselves at risk. This is just one example of how publication bias can have real-world consequences. So the next time, and this is really the bottom line, when you read a study, dig deeper, question the findings, and remember, always be skeptical. Until the next video, have fun. This lecture will kick off the journey on how to compute and analyze hypothesis testing results, and in brackets, with a known population variance. Before we begin, let's make sure that we are on the same page. A hypothesis is a statement or assumption that we want to test, and variance is the measure of how spread out a set of data is. In this lecture, we'll be focusing on how to test a hypothesis when we know the variance of our dataset, and this means that we use the Z distribution. And to really nail this down, let's look at a couple of examples. The first one, you are a quality control engineer. You're responsible for the production of wooden chairs at IKEA, and recently you're not super satisfied with the chairs. They feel heavier than usual, implying that there is more wood than planned in each chair. Now, this is what we know. Population mean weight is 12 kilos, and the standard deviation of product weight is 0.5 kilos. Therefore, the null hypothesis, or our status quo, it will be that the average weight of each chair is 12 kilos. And therefore, the alternate hypothesis would be that the average weight of each chair, it's not 12 kilos. So one is the opposite of the other. And to test our hypothesis, we would like to have a 95% confidence level. Finally, we collect a sample of 100 products from the manufacturing process. And we have all the data that we need in order to do it. The general process first, and then the calculations, starting with the process. By calculating the z-score and comparing it to the z-distribution table, or in Excel, our functions in Excel, we can test the hypothesis and determine if the new manufacturing is producing products within the desired range. Now, let's apply this and actually go into the details. First, we know that our sample is 100 products, and the sample mean weight would be 12.4, for example. And now let's use and compute our z-score, which is the mean of the sample minus the mean of the population divided by the standard deviation of the sample divided by the square root of the sample size. And all of this gives 0.8. So this is a formula, and what we need to do is to then find this, z-score in the z-table to find the probability, which in our case would be around 0.21. Now, what we do is that we use this probability to reject or fail to reject the null hypothesis. Now, we would take this 0.21 and then to compare with our confidence level. In this case, if it were below 0.05, we would reject the null hypothesis, and we would conclude that the production is not within the desired range of weight, so the 12 kilos. However, it is above 0.05. Therefore, we would fail to reject the null hypothesis, and we would conclude that the production weight is indeed similar to 12 kilos. And, just to recap, if the probability would be below 0.05, then it would be very likely that the weight is no longer the 12 kilos, that there's something off with the production. But because it is, we cannot really conclude it. It's very likely that the production, so the weight, is very similar to 12 kilos. Now, I know that this can be complex, so you are going now from an IKEA chair producer to a market researcher, and you want to see what is the average age of the customers. And the current status quo is that they are 30 years old, and you want to test this hypothesis with a 90% confidence level. You have the standard deviation, which is 3. Your sample is 50 customers. Now, the process is the same. You test the hypothesis by calculating the z-score and comparing it in the z-distribution table, or in our case, with our Excel functions. Now, let's go through the process once more. We know that our sample is 50 customers and that our sample mean age is 29.5. Next, we use the standard deviation of the customer age, which is 3, and we compute the z-score, which is the mean age of the sample minus the mean of the population, which is 30, divided by the standard deviation, divided by the square root of the sample size. And we get minus 0.17. Now, we use this minus 0.17 to find the z-score, and we find that the probability would then be 0.44. Now, we would use this 0.44 to determine and assess the hypothesis. And the null hypothesis, I would recall that the age of the customer is 30 years old. Now, since the probability is above 0.9, because our confidence level was 90%, we cannot reject the null hypothesis. And we cannot conclude that the age is not within the range of 30 years old. To sum it up, in this course, and in this section in specific, we are going to over the steps and calculations that you need to perform in order to test a hypothesis, in this case with non-variance, and what we definitely need in order to make this happen. We need to collect a sample. We need to have the sample mean, the sample of the population, and the standard deviation of the population. As a last step, we find the z-score, we compare it in the z-distribution table or with our functions, and this is it really. I know I've talked enough, so let's put something into practice. Until next video, have fun. Welcome to the case study briefing on the production of the Tesla Model X. I'm here to guide you on this very exciting journey that connects hypothesis testing to the real world. Now, of course, you may wonder, why are we doing this? What does car production have to do with hypothesis testing? Well, let me tell you. I really think this case study is a game changer for your understanding of statistical analysis. You see, when it comes to produce something as complex and high-tech as the Tesla Model X, it's very important to ensure that every single car that rolls off the assembly is free of defects and meets the highest quality standards. And this is where hypothesis testing comes in, so that you step by step make little improvements so that you achieve maximum quality and zero defects. And what are those elements? For instance, they can be the production line, weather conditions, number of workers, and so on. By the end of this case study, you'll have a solid understanding of how to apply hypothesis testing in several different scenarios based on your hypothesis and based on the data that you have. But don't get me wrong, I know that this can be difficult, and oftentimes it can seem counterintuitive, but trust me, I really try to make this different, and I'm going to guide you step by step on how to apply hypothesis testing. And that's it, really. Let's learn, and until the next video, have fun. Alrighty, time to kick off our hypothesis testing now with Excel. And for that, please come to the folder that I've shared with you, then to the hypothesis testing folder, and then click on the Tesla X Excel file. And here we can actually kick it off. So let me show you what we have. We have the data here, so the production date, the number of defects found, the number of cars produced, the weather condition, and the number of workers on shift. And then we have two big types of tests. We have the two-tail tests and we have the one-tail tests. And then for each we'll have four types. When we know the variance, when we don't know the variance, when it's the paired t-test, and when it is a two-sample t-test. And they're very similar between the two-tail and the one-tail. Of course, there is some difference, but they're very, very different, which is good because we actually get to repeat the general logic from one to the other and, of course, adapt. But don't worry about it. We'll go through it step by step. In each case, there is a situation, and it's our goal to take the situation and make hypothesis testing out of it. So let's kick it off. And the situation goes and reads as follows. You have invested thousands of dollars per employee to improve their satisfaction and productivity. Your goal is to improve from the average of 54 cars produced so far with the corresponding standard deviation of the population of 2. Now, Elon Musk, who is the CEO of the company, believes the opposite, that the benefits and other factors like the constant raining are hurting production due to constant sickness. You can see here that at least in most of the days, at least at the start, it was raining. And therefore, just to wrap it up, we have an agreement on the confidence level that is 95%. Now, the null hypothesis. we have here that we want to improve from the average of 54 cars. Therefore, null hypothesis is the average number of cars produced. So average number of cars produced is 54. And therefore, let me actually put this is in bold. The alternate hypothesis would be the opposite. So the average number of cars produced is not 54, because it's always the opposite. Next, we also have some data in the situation. If we want to improve from the average of 54, then the mean of the population will be 54. And we also have a standard deviation of the population of 2. Here we go. We write here at 2. Next up, we have mean of the sample, so average. And then we go to the data, and then we get here cars produced, which is column C. And we have the sample. We use the function count. We go as well to data, cars produced, and we can close it. Next up, we have the z-score, and let me add here a parenthesis that it is missing for the formula. So the way that this works, so equals, and we have x minus x bar, which is the mean of the sample minus the mean of the population. Close parenthesis, divide, open parenthesis once more. We have the standard deviation of the population, which is B3, and then we divide by the square root of the sample size. Close parenthesis, and here we go. Now, we need a formula for the p-value, and this is actually one of the main differences between the two-tailed tests and the one-tailed tests. And this is what I actually want to show to you. And here we need to start with the norm S, and let me check which one it is. And here you go. So it's the norm S dist. We include the Z, which is in our case what we just computed, and cumulative is always equals to true. Again, I've not seen anything that indicated, or I've not seen a situation where you don't actually use true. Of course there are, but not in the average business situation. Now we have the p-value here, which is indicated to 1, but there's something more to this formula. So to compute the p-value, you do 1 minus, and here you go. And then the key difference between the one-tailed test and the two-tailed test is that you are going to multiply all of this times, oops, and this is not what I want. You multiply everything times 2. And here you go. So we have the p-value, it's 0.00, and it actually takes quite a few decimal cases until we get a digit other than 0. But I don't want you to recall this formula. So the most important thing is that you need to input these here, right? Let me put them as yellow. This is important, right? So these are values that you need to include. This is a formula. So this stays here. And the p-value, this also stays here. You just need to know that it is a two-tailed test. And then finally, you have the p-value reader, because these are just numbers, but I want you to focus on the interpretation of this. This is the most important thing. And I also want this to be a function. So if, and then if the p-value is bigger than 0.05, which is our currently agreed confidence level, what you write is you cannot reject the null hypothesis. And here you go. And otherwise, you reject the null hypothesis. Here you go. Close parenthesis. And here we have it. And what we have here. So we have that the null hypothesis is 54. And with this current sample mean and the sample size and every other data point, we reject the null hypothesis. And therefore, it's very likely that this current investment, those thousands of dollars to improve employee satisfaction and productivity, is most likely yielding results, because it's unlikely, and in this case the mean of the sample is 55, it's very likely that the current production is above 54. And this is the general conclusion. Bottom line is, you need to know what kind of test you have. If you have non-variance, come here. If you have a two-tailed test, come here. Input here these numbers, and then you get a result. And this is the most important thing. This is it. Until next video, have fun. Hey everyone, welcome to our video on hypothesis testing when the variance is not known. Now, you might be thinking, oh great, hypothesis testing with suspense. Awesome, just what I needed. But trust me, this is actually way easier than you think. If you understood how it worked when the variance is known, the only difference when the variance is unknown is that we use the t-distribution. Very similar to when we were doing the confidence intervals and we just replaced the z-distribution with the t-distribution. It's the same. So it's going to be very easy, and I hope that you'll also see it as well. Let's go for our example. Let's say that you are a chicken farmer and you want to know if your chickens are laying the same amount of eggs as the average chicken. So this is your problem statement. You take a sample of 15 of your chickens and measure the number of eggs laid in a week. The sample mean, let's say it's 6.5 eggs per week. And the population is assumed to be 6 eggs per week. Now, you need to figure out if your chickens are laying the same amount of eggs as the average chicken, or if it is statistically different. And this is where the hypothesis testing comes in. The null hypothesis is that the mean, so the production, is equal to 6 eggs per week. So this is the status quo. And the alternate hypothesis is that the production is not equal to 6 eggs per week. And the general process, as you'll see, is the same. The formula is very identical, with the distinction that when the variance is unknown, we use the t-distribution, because we use a t-test. This is what it is called. So please get your Excel ready, because we are about to do something very similar to before, with just this one change. Until the next video, have fun. Let's kick off this part on hypothesis testing now when we don't know the variance, and still for two tails. Let's read the situation. Social media has been all over Tesla. The engines from a couple of cars started to catch smoke. Even worse, the cars were from high-profile customers. You talk to your employees, who tell you that the number of defects is within the normal average of 2.2. You decide to investigate the situation yourself. Now, since the car production has suffered many changes in the past few months, there is very little data on the population. Therefore, let's go to the null hypothesis, which is that the average number of car defects is 2.2, and the alternate hypothesis would then be that the average number of car defects is not 2.2. So pretty clear. So is not, and let me put this in bold so that it's very, very clear. And here we go. Now, we don't really have data on the standard deviation of the population, so NA, and this is why we are here. The mean of the population, what we want to achieve is 2.2, so this is clear. Mean of the sample, we need to find that out, so average, here we go, and we go to our data, defects, and close parenthesis. And here you go. We have 2.36, which is slightly above, but of course we need to answer this from a statistical perspective. Let's go and get our standard deviation of the sample. So stdev.s, go to the data, and then column C. And we also need to have the sample. So we need to get counts, and then we go to our data and also the defects found. Here we go. Next up, we need to do not the z-score, but rather the t-score. And let me add here some parentheses as well. The formula is exactly the same, but now we have, or we are using the standard deviation of the sample. So that's the main one. So let's do it, and parentheses. So mean of the sample versus the, or minus the mean of the population, divided by, and then open parentheses, standard deviation of the sample divided by the square root of the sample size. So close parentheses, and here we go. So 0.5. Let me also change here because this should be sample. And now, yes, it's more correct. And now we need to get this probability, which is done using this t-dist for the two tails. And the way that this works, so the x is this 0.5, comma, degrees of freedom is the sample size minus 1. Close parenthesis, and here we go. And as I was reviewing this, I noticed that I got the wrong standard deviation. So let me do that from scratch. So stdev of the sample, and let's go to our data, and it should be the defects found, close parenthesis, and here we go. So we get this, probability, which is, our p value. Here we go. And now we need to, read and interpret this. And what I can do is very simply, I copy this, Control C, and I come here, Control V. So we cannot reject the null hypothesis. This means that even though the mean of the defects is slightly higher, it is not that high that it enables us to tell and to say that we are getting more defects now than in the past. So this is it. I hope you enjoyed this video on how to compute hypothesis testing with and on variance and two tails. Until next time, have fun. Welcome to the lecture on paired t-tests, also known as dependent t-tests, which are a type of statistical analysis that are used to compare the means of two related groups. They're often used when you want to compare the before and after of an experiment, or when you want to compare two groups that are closely related in some way. Now, let's say that you are a mad scientist who just created a potion that you believe will make people run faster. You are so convinced that this potion is the real deal that you decide to put it to the test. You round up a group of your lab rat friends and have them run a 100-meter dash. You time them and record their results. Then you make them drink your potion and have them run the same 100-meter dash again. After they're finished, you take the before and after results and you use a paired t-test to compare the mean running times of the group before and after drinking the potion. The t-test will help you determine if there is a statistically significant difference in their running times, and if your potion is actually making people run faster. Another example, now a business one, of when a paired t-test might be used is in a marketing study, where researchers want to see if a new advertisement is more effective than an old one. They might take a group of participants and show them the old advertisement, then show them the new advertisement. Then they would use a paired t-test to compare the mean effectiveness of the two advertisements. And finally, they would determine if the new advertisement is more effective or not. Now, let's go deeper into the formula. The way that it works, so the t-value is the delta between x1, so x bar 1, the average of x1, minus the average of x2. Then you divide everything by the standard deviation of the differences, and you divide by the square root of the sample size. Let's recap. x1, we have the mean of x1. Then we have the x2, which is the mean of the second group. And therefore, in the first part, you are doing this delta. The delta of x1, of the average of x1 minus the average of x2. Then SD, standard deviation, but of the difference between the two groups. And then finally, N is the number of pairs, so the sample size. Most importantly, we'll actually be doing all of this using Excel because particularly as we take on the standard deviation of the difference, it actually becomes more complex, but I'll show you 2 times how to do it using Excel, and that's the most exciting part. Now, let's continue. The paired t-test works by comparing the means of 2 related groups and determining if there is a statistically significant difference between them. It assumes 2 things. First, that the 2 groups are independent, for example, that the same participants are being measured in both groups. And the second thing that it assumes is that the differences between the 2 groups are normally distributed. The way that the process works is that we calculate the t-value with a formula that I showed you, and then we compare it to the t-distribution with n-1, so n being the sample size, n-1 degrees of freedom. Now, let's recap, and to sum it up, paired t-test is a very powerful tool that can help researchers determine if there is statistically significant differences between 2 related groups. And by comparing the means of 2 groups in a controlled and systematic way, researchers can gain valuable insights into the effectiveness of a new drug, advertisement, or anything. And that's it, really. Until the next video, have fun. Let's apply what we have learned now with a paired t-test, still with 2 tails only for now. Let's go through our situation, which I'll read. The sales department has been very critical of Tesla recently, saying that they have been getting many complaints from customers that claim that the car is taking longer than expected. Your department, on the other hand, says that the production has been stable over time and going according to plan. They fire back and say that the sales department has been selling too much. And then you decide to take initiative to see if the production has been stable in the past 2 months. Now, this is a paired t-test, and therefore the null hypothesis, so the most simple one, is that the production in month 1 equals production in month 2. So this is the status quo. And then you have the alternate hypothesis, which is that the production in month 1 is different than production in month 2. So this is how we would phrase it. Now, I've prepared a couple of things here already so that we can follow. So of course, like the first thing is to actually compare the averages. So average between month 1 and month 2. So here we go, column B first, and then we do the same. So average, and now we get column C, close parenthesis. Here we go. The challenge for us is really to figure out if this is statistically less in a significant way. Now, we need something special. So I would like to show you one add-in for Excel. Maybe you know, maybe you don't know. So please come here to File, and then Options. And then in the add-ins, click on Excel add-ins, go, and then we get the analysis tool pack. Here we go. You can see it here. Now, this data analysis is wonderful. It has a lot of things, a lot of different options, including some things that we have already done, for instance, correlation, covariance, descriptive, statistics. Insofar, I've just shown you the formulas. I think they are as okay as doing this. The key difference is that we are working more in a click-based way. And for us specifically, we have here the t-test, z-test, and also t-test of 2 samples. I know that this is very tiny, but this will be zoomed in. And for this case, of course, we have done the z-test, but our goal is really to do the t-test per sample for 2 means. Let me click on OK. And now let me get here. So let me get variable 1 range, which for us is the column B. I need to pick the actual values. I cannot just select the whole column, but just the ones that have values. And then labels, because the first row has labels. And then output range. You can see that I have selected here already something. And this is where we want to include. So here we go. Let me click on OK. And this is how you do a paired t-test. Now, the output. We have the mean, right? So 55.6 and 54.5. So this is clear. We also have the variance, number of observations, correlation, and the degrees of freedom. And what's most important for us is really the 1 tail and the 2 tail. We're still just doing 2 tails, and therefore we look at the p-value for the 2 tails. If we're doing for 1 tail, we would look at this value. But currently, we look at this one because we are doing 2 tails. Another thing that I like to do is that I really dislike decimals for some reason. I like to simplify this because, I mean, there's no reason to have more than 2 decimals. No reason whatsoever. And I think this looks better. So we have our p-value reader for null hypothesis here. And I promised that I would show you 2 ways. So this is the second way in order to do this paired t-test, which is the formula. So t.test, open parenthesis, and then here, what we need to pick is first array, then we get the second array, comma. Then, is it a 1-tailed or a 2-tailed? It is a 2-tailed. And then type. And here we have 3 things. So we have paired. We have 2 sample with equal variance. This is something that we need to see still. And also the third option, we also still need to see, which is with unequal variance. And for us, we are doing a paired. And here you go, close parenthesis. And here we have it. And maybe you can see, but most likely you cannot anymore because I decreased the number of decimals, but these values will be the same. So 35743, and here we have 35743. So in case that you don't really like to use the tool pack, you can use a function like I've shown you here. Now for the reader, here you go. So if, how does this work? So if this value is bigger than 0.05, and here we write cannot reject null hypothesis, and inversely, If it's less than, reject null hypothesis. And this would tell you that they are different and that there was a decrease in the production in month 2 versus month 1. And this is it, really. I hope you enjoyed this. Of course, in case that you have any questions, feel free to use the Q&A. Until the next video, have fun. Let's talk about two-sample t-tests, which is a statistical method used to determine if there is a significant difference between the means of two different groups. It's a powerful tool that can be used in a variety of contexts, including business, science, and pizza. Let's start with this funny example. Imagine that you're trying to determine if there is a difference in the amount of pizza consumed by people who watch horror movies versus those who watch romantic comedies. You randomly select 20 horror movie watchers and 20 romantic comedy watchers, and you measure the amount of pizza they eat in a given night. You then use a two-sample t-test to compare the means of the two groups. Now, this is the framework, and now let's go into more details on how to build it. You randomly select 20 horror movie watchers and 20 romantic comedy watchers. You measure the amount of pizza they eat in a given night. Then, let's assume that the mean amount of pizza consumed by horror movie watchers is 3 slices with a standard deviation of 0.5 slices. And for the romantic comedy watchers, the mean is 2 slices with a standard deviation of 0.4 slices. You then use a two-sample t-test to compare the means of the two groups. And let's say the test statistic or t-value calculated is 3.4 and the corresponding p-value is 0.0013, so less than 0.05. Since the p-value is very low, we know that we need to reject the null hypothesis. And in general, the null hypothesis, as we know, is that there is no difference between the status quo. And therefore, in this case, for exemplification purposes, is that there is a statistically significant difference with horror movie watchers consuming significantly more pizza. Now, who would have thought that horror movies would make people so hungry? We talked about pizza, but we can also look at it with a more serious example of a two-sample t-test in a business context. Imagine that you are a marketing manager for a company that sells a new product. You want to determine if your new product is more effective at increasing sales than your old product. You randomly select 20 customers to use your new product and 20 customers to use your old product. After a month, you measure the sales of each group. You then use a two-sample t-test to compare the means of both groups and assess if they're different or not. Now, one important thing is to assess if the variances are similar or not. The two-sample t-test assumes that the variances of the two groups are equal. If the variances are not equal, you may want to consider using a different test, which is called the Welch's t-test, which does not assume equal variances. Now, don't worry, I will show you how to do this in Excel, all of it, no worries. Now, I think the more interesting question to understand is, okay, how do I know if the variances are different? Like, how do I assess it? And the way to do it is that you can use the ratio of the variances. This is called the F ratio, which is calculated by dividing the larger variance by the smaller variance. If the ratio is close to 1, it suggests that the variances are similar. If the ratio is significantly different from 1, it suggests that the variances are not similar. And now you may ask, okay, What do you mean close to 1? Isn't there like a metric? And yeah, there is a metric. No worries. I'll show you in Excel how to do it. This is called the f-test, which I'll show you how to interpret as well, so that it becomes very clear what to do and how to do it. Now, as you can see, two-sample t-test, very powerful tool that can be used in a variety of contexts, from pizza to business. It requires equal variances that we need to test beforehand. Otherwise, there's another test, which is called the Welch's t-test. In Excel, this is very, very similar, but it's very important that you also understand that there are different tests, whether you have the variance or not, whether they are similar or not too. And then finally, to do it, we would use this F ratio, which I'm about to show you how to actually do it. This is it, and let's keep it going with our practice video. Until then, have fun. Okay, so this is the last video on the two-tail tests. Let's go through our situation. The Tesla factory you manage has 2 shifts during the day. You are present during shift 1, but not during shift 2. Your second in command told you that shift 2 is doing great. Now, you are aware that to prove to the senior management that both shifts work with similar productivity, you need to show them with numbers. And of course, nothing is better than hypothesis testing. What is the null hypothesis? What is the status quo? The status quo is that both shifts have similar productivities. There you go. Remember, null hypothesis, there is no difference. It's the status quo. There is no difference. And as a result, the alternate hypothesis is that productivity of shift 1 is different than shift 2. Now let's compute here the mean and the variance. So this is important for us. And here you go. So average of shift 1 and then average of shift 2, so column C. And shift 2 has indeed lower average of productivity, but of course we need to talk about variance. So var of the sample, could also use standard deviation here, of course. I'm just showing you the variance. And of course, shift 1 first, and then the var of the shift 2. I'm showing you here the variance and not the standard deviation, because when we do the f-test, one of the outputs is the variance, not the standard deviation. And just for you to see what we are currently getting here is the same what we do with the functions. So that is the general goal. Now, shift 2 has a much higher variance, and this is what we need to watch out for. To do the f-test, this is what we need to do. We go here to our data analysis, and then we get our f-test. So f-test to sample for variances. Then we need the range 1. So here you go, Control Shift arrow down and close it. Then repeat the process for the shift 2. And I would highlight, or better yet, let me finish this and I'll continue my highlights. And output range is that we can put it here. So just to replace this part. And let me put here OK. And here you go. Now, one thing that I want to show you first is that I'm doing this wrong on purpose. When you are doing this f-test, in the first array, you should put the one with the higher variance. And this is one of the reasons why we did it here. Therefore, we need to switch them in order to get a good analysis. So go to the data analysis f-test, and so I'm going to do controls, or better yet, let me just do it from scratch. Shift 2, control, shift, and then arrow, and then repeat the process. And here you go. Now let me close this part. The output range is the same. And let me click on OK. And here we go. Before I get to this, let me just show you one thing, which is that we don't have the same length. And this is okay for two samples. This is definitely okay. When you're doing the pair, that was not okay, but this is fine. And this is how you should be doing it. It's okay to have, different sample sizes. Now, the way to actually interpret this, and of course, this is not trivial, but if this f-test is bigger than the f-critical one-tail, then the variances are not similar. And otherwise, variances are similar. So this is how to do it. The most important thing is that you understand that when you have two samples, you need to do this f-test first, with the variance being in the first array. And then use this f-test interpreter to check which kind of t-test you can do. And the variances are similar by this, which, to be honest, it was a bit unexpected because there's a big delta in the variances, but it is what it is. Therefore, what we do is that we go to our data analysis and we have two sample assuming equal variances. And this is what we do next. We go here, we get our shift 1, and then we get our shift 2 labels, and then output range. I'm going to select this one here, and here you go. Let me click on OK, and something is missing because the variable to range did not end up here. So let me put here the column C. So the range 1 disappeared kinda. So let me do it once more, and now it should work. Let me click on OK, and let me overwrite, and let's have a look. Now we are still doing a two-tailed test. So we look here, p-value very, very tiny. Therefore, we would reject the null hypothesis. And let's compute and let's create once more our p-value reader. So if, and to tell, so if this is less than 0.05, we keep going with our confidence level of 95%. We reject null hypothesis, and otherwise we fail to reject null hypothesis. This is the most important thing. And of course, as you trace back from what we were doing, right? Because we always start by stating the hypothesis, and at the end we make a conclusion. Last thing I want to show you is the two sample and then t-test, because you can also do it without the data analysis toolpack. So t.test, let's get our array 1. So here we go. Let's get the second one. Here we go, comma. Then we go here. Let's go back. It's here. It's asking us what kind of tails we have. We have 2. And then what kind of test. And we have 1, which is assuming equal variance. Close parenthesis. And here we go. And we get a similar value to this one. Let me add one more decimal case. And here we go. So this was it. As you can see, again, 2 different ways of computing it. The most important thing is that please use these templates, because they're very helpful. And I don't know this by heart, right? So I have these temples that I have built and that I use when I need for hypothesis testing. Most important thing is that you understand what you're doing. And this, mechanical part, calculations, let the software do it for you. This is it. Till next video. Have fun. Hey there, are you ready to take a wild ride into the world of one-tail hypothesis testing? Well, buckle up, because we're about to go on this statistical adventure. But first things first, let's define what the one-tailed hypothesis test is. It helps you figure out whether your sample mean is significantly different from the population mean. And, this you already know, but in just one direction. It's worth noting that within one-tailed hypothesis testing, there are two subtypes, left tail and right tail. A left tail test is used when the alternative hypothesis is that the sample mean is less than the population mean. Left tail, less than. And the right tail is used when the alternate hypothesis is that the sample mean is greater than the population mean. Right tail, greater than. This is important for you to, in a sense, have this in mind. But this is how I memorize. Left, less than. Right, more than. And now let's go with one example. Let's say that you are a farmer who grows orange trees and you want to know if your orange trees produce more oranges than the average orange tree. Remember, you're comparing an average of a sample to an average of a population. So it's not a pair t-test, it's not a two-sample t-test, it's one of the others. And what you need to find out is, okay, so you take a sample of your orange trees. This you always need to do. You count the number of oranges that they produce. And if you have, you can compare your sample mean to the population mean of orange production for all orange trees. So by having the data, you can, in a sense, trickle down and figure out what kind of hypothesis testing you can do. And then to conclude, so if your sample mean is significantly higher than the population mean, you can conclude that your orange trees are cypress superstars. In this scenario, you'd use one-tail test, specifically a right-tailed test to determine if your sample mean is significantly greater than the population mean. Your alternate hypothesis would be that the sample mean is greater than the population mean. Null hypothesis is then that the sample mean is less than or equal to the population mean. So what's the real difference here? Well, it's all in the direction, really. So a two-tailed test is like this superhero with 360-degree vision. So it's looking left and right. It looks at all sides of the coin. And a one-tail test, on the other hand, is like a superhero, but with very good tunnel vision. So it just looks at parts of it. So it just looks at one of the tails. Furthermore, it's also worth noting that there are some key differences. In a two-tail test, the confidence level is associated with both tails of the distribution, as we're interested in determining if the sample mean is different from the population mean. In either direction, it's fine. This means that the confidence level is spread evenly across both tails. For example, if we're using a 95% confidence level, it allocates 47.5% to each of the sides. And implicitly, we have a 2.5% margin in both tails. In a one-tail test, the confidence level is only associated with one tail of the distribution, as we're only interested in determining if the sample mean is greater or less than the population mean. To conclude, one-tailed hypothesis testing is a great tool for comparing a sample mean to a population mean in a specific direction. The full margin of error is allocated to one tail, and we can use one-tail tests for the t-tests for the paired t-test, for the two-sample t-test, we can use for all of them. And this is exactly what we're going to do starting in the next video. Until then, have fun. Let's kick off our one-tailed tests. And in this video, we'll do the one-tailed test with known and unknown variance. And in the next video, we'll do the paired t-test and the two-sample t-test. As you'll see, it's mostly a repetition of what we have done so far. There are a couple of differences. One of them is the hypothesis, how you frame them. And then the second one is how you actually read the p-value and how you compute it. That said, let's kick it off. We always start with reading the situation. It goes and it says, you have invested thousands of dollars per employee to improve their satisfaction and productivity. Your goal is to improve from the average of 54.5. That is your benchmark, your target, with the corresponding standard deviation of the population of 2. And Elon Musk believes the opposite, that the benefits won't increase the productivity. So what do you want to prove? And another thing, at least from my side, it's easier when we're doing one tail to start with the alternate hypothesis. In our case, we want to prove that we have improved the car production. So car production is bigger than 54.5. And therefore, the null hypothesis is the opposite. Car production is less than 54.5. And one thing that I would also like to clarify that is important, I can put here bigger or equal than. There's no big difference. Actually, there is no difference here. Of course, mathematically, you could say that, yeah, they are slightly different, but from an hypothesis testing perspective, it doesn't change. And with this, let's also take a few elements. Standard deviation is 2, and this mean, so this target that we want to beat is 54.5. And then we have the mean of the sample, so average. And here you go, open parenthesis, we go to our data. We get our column C, and we also need a sample, so count, and we get our cars produced as well, 55, that is our sample size. And then here, let me add here some parentheses, because we divide by this together, and now we can kick it off. So equals, and mean of the sample minus the mean of the population, divided by, open parenthesis, the standard deviation, divided by the square root, open parenthesis, and the sample size. Here we go, 2.26. Now, to start and to compute the p-value, we start with a norm sdist function, here we go, where we include the z-score, and cumulative is set to true. Here we go. And then the last thing for the p-value computation for a one-tail test is 1 minus this norm sdist output. If you recall, when we're doing the non-variance with two tails, we multiplied everything by 2, which we're no longer doing because it is just one tail for us. And lastly, we have our p-value reader, which I'll actually just copy here. I'm hopeful that you know this by heart. So if it's less than 0.05, and of course confidence level is implied to be 95%, if the p-value is less than 0.05, you reject the null hypothesis, and otherwise you fail to reject the null hypothesis. And here we go. So this is it. To conclude, what we have here is that our productivity is likely now to be higher than the 54.5. And currently we have proved that our incentives are currently working. Let's go to the unknown variance with one tail. And here you go. Let's read the situation. Social media has been all over Tesla. They say that more and more people are complaining about defects. They claim that improvements are urgently needed. You talk to one of your employees who tells you that the number of defects is within the normal average of 2.4, maybe even better than that. You decide to investigate the situation yourself. Since the car production has suffered many changes in the past few months, there is really no data about the population. So standard deviation of the population is NA, and this mean of the population or target that we want to achieve is 2.4. Then we would move. So alternate hypothesis, so this is what they claim, is that defects is bigger than 2.4. And the null hypothesis is that the defects is less than 2.4. And with this, we can actually continue. So we need to compute the average, standard deviation, and also the sample. So here you go. You compute the average first, and then the standard deviation of the sample. So stdev.s, open parenthesis, and let's put our column B from the data. And here you go. And then lastly, the sample size. I'm going faster. I hope that's okay. It's because we have repeated this before. So I'm trying to speed up because I don't want it to be boring for you as well. So the process of getting an average standard deviation, hopefully that's clear. If it's not, as always, please let me know. Next up, we have this t-score. And with this, what we compute is we use the same formula. So we open parenthesis, mean of the sample minus, and then we have the mean of the population. And then we divide everything by the standard deviation of the sample divided by the square root of the sample size. And I'm getting here an error, so divided by, and parenthesis, parenthesis, and let me close it. One thing that I'm noticing here currently is that we have mean of the sample is already below the mean of the population. So this is true, right? So this null hypothesis is definitely true, right? Because if the sample is already less than what we want to achieve, that's good. So let's try a different value here for the mean of population. So to make sure that we are doing it right. So 2.2 and 2.2 here as well. And let me change it here in the text. So we get this t-value, and we are doing this alternate hypothesis bigger than. So this is the right tail. And therefore, we go with our t distribution. And then there's this function, which is the right tail. And we include the x, which is the, the t-score, the t-value, and then comma, degrees of freedom, sample size, -1, and here you go. Let me click on enter, and we get this p-value of, 13.26% or, 0.13. Let me copy our p-value reader. So Control-C and Control-V. So cannot reject the null hypothesis. And therefore, even though it's higher than this target value of 2.2, because of the standard deviation, it does not allow us to say with statistical significance that the number of defects is now higher than what we wanted it to be. And that's it, really. I hope that is clear, and that this one-tail test, which I often find to be trickier, or at least when I was learning, I had a bit of issues understanding it, but I hope that I was able to, communicate how they work. Until the next video, have fun. Alrighty, let's go to our part 2 on the one-tail test. We start with a paired t-test, and let's go over the situation. The sales department has been very critical of Tesla recently, so the production, saying that they have been getting many complaints from customers that say that the car is taking longer than expected to be delivered and that production has slowed down in the previous month. Your department, on the other hand, says that the production is at least as good as before. The historical pattern is that productivity increases over time. So what is the alternate hypothesis that the sales department is getting at? That production of month 2 is less than production of month 1. And, we have the null hypothesis, and we have that production of month 2 is bigger than production of month 1. So here we go. Fairly easy to do this, I'm hoping. And here you go. Now, what we need to get at is this averages. So let's compute them. So we always start by doing the simple approach, which is, okay, you know what? Let's compute the average between month 1 and month 2. So month 1 average, column B, and here we go, month 2 average, and we go here to the month 2, and we compute it. And we see that it is less. The question is really, is it statistically less than month 1? And for that, we can do a t-test, a paired sample for 2 means. I really prefer to do and to use this data analysis toolpack whenever I can, instead of actually using the functions, because I think it's a bit easier, at least from my side, because it's click-based, so it's telling you what to do. You have already picked the test, so it's not something that you need to figure out with a function. And here we go. So we have here the variable 1 range, variable 2 range, and labels yes, and then let's put it here in the N5 as the output range, and that's it. Because it's a replica of what we did before, so everything was kind of here already. You can change here the alpha, right? So the confidence level, this is something that you can choose here. And let's click on OK. And yes, so it's asking us to override. Let's click on OK. And here we go. Now we have here the mean, the variance, and we also have here the p-value. And we are doing a one-tail test, so we focus on the p-value for the one tail. And let me highlight it here. This is the one that you do. And you have here the p-value reader for null hypothesis. So if this value is less than 0.05, you reject null hypothesis, and otherwise you fail to reject null hypothesis. And here you go. So let's close parentheses. So currently we are rejecting the null hypothesis. And as a result, we favor the alternate hypothesis that the production in month 2 is statistically less than the production in month 1. And therefore, even though your colleagues in your department is saying that, production is at least as good, there is no data that supports that fact. And this is it, really. So let's do the 2 sample test, 1 tail. And let me zoom in. So here we go. We have, and let me read the situation. So Tesla factory, you manage as 2 shifts during the day. You are present during shift 1, but not shift 2. You have your second in command who tells you that shift 2 is doing great. In fact, her recent incentives led to higher efficiency during the second shift. Let's check if that is true. Alternate hypothesis is that we have that shift 2 production is bigger than shift 1. And alternatively, null hypothesis is that shift 2 production is less than shift 1. Here we go. Let's start by computing, the means. So average, and then here, let's just get the column B, close parenthesis, and same thing for the shift 2. And here you go. So we have 64 as the average production, and in terms of an average, it is bigger. And now we need to check if it's definitely bigger. We also need the variance. So, and variance of the sample. Let's get here column B. And then we compute the var of the sample for column C. Here we go. And we have that the shift 1 has slightly higher variance. This is important because now we need to do the F test. And this is what we are going to do now. F test. Remember that we need to do the F test to figure out if our variances are similar enough. If they are not similar enough, what we need to do is that we use a different type of t-test. And here you go. So F test is here. Let me get the data. So the first one is the one with a higher variance, which is column B. And then the second one is the one with the least variance. Here you go. And I want it to be here, yes, on S1. And labels, yes. And here we go. So press on OK. And we have that. I mean, the variance is very, very similar. And therefore, let's use our F-test interpreter. Let's get it from our 2-sample t-test before. And let me do Control-C, and then here Control-V. And I would recall that if this value is bigger than the F-critical 1-tail, so if F bigger than F-critical 1-tail, variances are not similar, and otherwise variances are similar. And I mean, I don't recall this all the time, right? So I always use this interpreter that I have, and I try to use these templates as much as possible. And now that we have, and that we know that the t-test has similar variances, we can actually use the other t-test, so 2-sample assuming equal variances. And let's put here, so let me select the column B, and then select the array from column C, and labels yes, output range would be S13, and this is it really. So press on OK, and here you go. We have that our p-value for 1 tail slightly above 0.05, so we don't really have concrete data to support the alternate hypothesis, and currently we are failing to reject the null hypothesis. But let's get our p-value reader, Control-C, and here, let me put it here, and let me just make sure that yes, it is the 1 tail that we're currently assessing. And we are, of course, failing to reject the null hypothesis, so we cannot say that the production in shift 2 is bigger than shift 1. We can say that shift 2 production is at least as good as the one in shift 1. And that's it for this journey into 2 tails and 1 tail hypothesis testing. I hope you enjoyed it. Until next video, have fun. Whoa, can you believe it is over? Well, I mean, it's 4 hours, right? Anyway, congratulations on getting here. It's a fantastic effort from your side, especially if you had the course materials, you followed all the course with me, did the challenges, all the exercises. It's a really proper effort. Now, for the gifts that I promised. First one, wonderful quote. It's by Drake. It says, "Started from the bottom, now we're here." It's a quote that I really enjoy. I have another one from Lil Wayne, another from Arnold Schwarzenegger. I'll probably share them in some other video. And for gift number 2, there's a free ebook on conjoint analysis that you can also get a link in the description. This ebook on conjoint analysis is a project. It's a step-by-step approach on how to apply it using Python. It's based on a real-life project, and conjoint analysis is a marketing research technique that can be used in order to infer what kind of feature can be added to a product. That said, I hope that you enjoyed, and I'm looking forward to seeing you in another video. Till then, have fun.